For centuries, humanity has carried a remarkably simple belief about the universe, given enough time, enough determination, and sufficiently advanced technology. Any destination should eventually be within reach. The stars may be unimaginably distant, but distance itself seems like a problem that can always be solved. Build a faster spacecraft, develop a more powerful engine, wait long enough, and even the nearest neighbouring star should one day become another place that human beings can visit. Modern astronomy invites us to look at that comforting assumption a little more carefully, because somewhere between the Earth and the nearest stars, distance quietly transforms into something else entirely. It ceases to be merely a matter of kilometres or miles. Instead, it becomes a conversation with the deepest laws of nature. A single light year is not simply a long journey. It is a frontier where energy, time, matter, and even the structure of space itself begin to impose limits that no amount of optimism can easily erase. This presents a curious paradox. Light, something so familiar that it fills every sunrise and every clear afternoon, crosses one light year effortlessly. It does so simply by continuing its endless motion through the vacuum of space. Yet the very civilization capable of splitting atoms, landing robots on distant planets, and building telescopes that peer billions of years into the past may find that following light, even for just 1 year of its journey, is vastly more difficult than crossing entire oceans once seemed to our ancestors. The paradox grows even stranger. Every year, new spacecraft leave Earth. Some travel farther than any machine before them. Others reveal distant galaxies whose light began its journey long before our own species existed. Astronomers routinely study stars hundreds or thousands of light years away with astonishing precision. In many ways, we have become experts at observing the universe, yet observing is not the same as reaching. The nearest star beyond our Sun, Proxima Centauri, lies just over 4 light years away. In cosmic terms, this is our immediate neighbourhood. If our galaxy were reduced to the size of Earth itself, Proxima Centauri would barely be a short walk away. It is difficult to imagine a closer destination beyond the solar system, and yet, no human being has ever travelled even 1/100th of 1% of that distance. No spacecraft currently moving through interstellar space is remotely close to reaching another star within a human lifetime. The probes Voyager 1 and Voyager 2, launched in the 1970s, have become symbols of extraordinary engineering. They have crossed the boundary where the sun's influence begins to fade into interstellar space. They are, quite literally, farther from Earth than any other human-made objects. But their achievement also reveals the scale of the challenge. Voyager 1 travels at roughly 17 kilometers every second. That speed is astonishing by everyday standards. Crossing an ocean at such velocity would take only minutes. Travelling from New York to London would require little more than the time needed to drink a cup of coffee across interstellar space. However, that remarkable speed appears almost motionless. At its current pace, Voyager 1 would need tens of thousands of years to reach even the nearest star, assuming it were pointed in exactly the right direction, which it is not. The numbers begin to stretch beyond ordinary intuition. Human history, from the first cities to the present day, occupies only a small fraction of that span. Entire civilizations have risen and disappeared in less time than Voyager would need, simply to approach another stellar system. It is tempting to respond with confidence. Technology improves, engines become more efficient. Future generations will surely build faster spacecraft. History certainly encourages such optimism. Sailing ships gave way to steam engines. Steam engines yielded to aircraft. Aircraft were followed by rockets that escaped Earth's gravity altogether. Every age has believed certain journeys impossible, only to watch those impossibilities quietly become routine. But there is an important difference between the obstacles humanity has overcome before and the one that lies between us and the stars. Crossing oceans demanded better ships. Crossing continents demanded better transportation. Escaping Earth required powerful rockets. Travelling 1 light year asks something much deeper. It asks whether nature itself allows such journeys to become practical. Regardless of how clever our engineering may become, that distinction changes everything. Many limits throughout history were technological. We lack the tools. Once those tools existed, the barriers disappeared. The challenge of interstellar travel may belong to a very different category. Some limits arise not because we have failed to invent the right machine, but because the universe itself operates according to rules that cannot be negotiated. Gravity behaves consistently everywhere we observe it. Thermodynamics does not suspend itself for ambitious civilizations. The speed of light appears identical no matter who measures it or how fast they are moving. These are not engineering problems waiting for better materials. They are the architecture upon which reality itself appears to be built. This documentary is an exploration of that architecture. Along the way, we will travel far beyond the familiar planets of our solar system. We will follow the discoveries of astronomers who first measured the staggering distances between the stars. We will examine the experiments that revealed an unexpected cosmic speed limit. We will explore extraordinary ideas ranging from nuclear propulsion to antimatter, from laser-driven sails to the mathematical possibility of bending space-time itself. Some of these ideas rest upon solid experimental foundations. Others remain elegant hypotheses. A few belong to the distant frontier where theoretical physics has not yet found definitive answers. Carefully separating what is known from what is merely possible will be one of our constant companions, because perhaps the greatest wonder is not that the stars are far away. It is that the universe has arranged distance, time, energy, and light in such a way that travelling even a single light year becomes one of the most profound scientific questions humanity has ever asked. Before we can understand why that journey seems almost impossible, we must first understand why our ordinary sense of distance fails so completely once we leave the familiar surroundings of Earth. That understanding begins much closer to home than the nearest star. It begins with the world we think we already know when we think about distance. Our minds are shaped by the world we evolved to inhabit. A journey across a city is measured in minutes. A flight across an ocean is measured in hours. Even travelling to the opposite side of Earth rarely requires more than a day. Our lives unfold within a scale where distance feels tangible, where every destination eventually appears on a map, and where the horizon is simply another place waiting to be reached. This quiet familiarity follows us into space. When children first learn about the solar system, the planets are usually arranged neatly across the pages of a textbook. Mercury sits close to the Sun, Venus follows, Earth comes next, with Mars just beyond. Farther out wait the giant worlds of Jupiter and Saturn, before the icy realms of Uranus and Neptune complete the picture. The illustration is wonderfully clear. It is also profoundly misleading. If the planets were drawn to scale, almost all of the page would be empty. Earth would become a tiny dot, barely visible against the vastness surrounding it. Jupiter, despite being the largest planet, would still appear surprisingly small. Between nearly every world would stretch enormous regions containing almost nothing at all. The solar system is less like a collection of neighbouring islands and more like a handful of tiny grains of sand scattered across an immense desert. Even so, the solar system remains our home. Because we have explored it for decades, its distances gradually feel manageable. Spacecraft have landed on Mars, orbited Saturn, flown past Pluto, and touched asteroids billions of kilometers away. Each new mission reinforces an encouraging impression that space, while large, is ultimately navigable. That impression begins to change the moment we ask a deceptively simple question. How far away is the nearest star? Not the brightest star in the night sky, not the centre of our galaxy, simply the closest star beyond our own sun. The answer is Proxima Centauri, approximately 4.24 light-years away. At first glance, the number seems modest. 4 is a familiar number. We cross 4 kilometers without much thought. 4 hours can pass almost unnoticed. Our brains instinctively attach ordinary experience to ordinary numbers. The word that quietly transforms everything is not 4. It is light-year, despite its name. A light-year is not a measure of time, it is a measure of distance. Specifically, it is the distance that light travels through empty space during 1 year. Light moves at approximately 300,000 kilometers every second. Not every hour, not every minute, every second. In the brief time it takes to blink, light could circle Earth more than 7 times. It races from the moon to Earth in just over 1 second. Sunlight reaches our planet in about 8 minutes. These numbers already hint at extraordinary speed, yet they still remain connected to places we know. Extending that journey across an entire year produces a distance almost impossible to picture, nearly 9.5 trillion kilometers. Written differently, it becomes approximately 9,460 thean kilometers. The mind searches for something familiar to compare against such a number, and finds almost nothing, even counting continuously. Speaking one number every second without ever stopping to eat or sleep, reaching 9 trillion would require hundreds of thousands of years. Numbers this large no longer feel like quantities. They become landscapes. Astronomers understand this limitation well. That is precisely why they abandon kilometers when discussing the stars. Units designed for everyday experience become too cumbersome once the universe reveals its true dimensions. Suppose we insisted on measuring the distance to Proxima Centauri in kilometers. Instead of saying it lies 4.24 light-years away, we would say it is about 40 trillion kilometers distant. The sentence becomes heavier without becoming more understandable. Light-years do something subtler. They remind us that distance and time are inseparable in the cosmos. Whenever astronomers describe an object as 1,000 light-years away, they're also telling us that its light began traveling toward Earth 1,000 years ago. Looking deeper into space is simultaneously looking further into history. Every telescope is also a kind of time machine. The moon appears as it was 1 second ago. The sun appears as it was 8 minutes ago. Jupiter is seen nearly an hour in the past. The nearest stars reveal themselves years earlier. Distant galaxies appear millions or even billions of years before the present moment. Space and time intertwine so naturally that separating them becomes increasingly difficult. This realization gently changes the night sky. The stars cease to be scattered points decorating darkness. Instead, each becomes a messenger carrying ancient information across unimaginable distances. Some of the photons entering your eyes tonight may have departed their parent star before a child was born. Others began their journey before modern civilization existed. The faint glow from remote galaxies may have started traveling long before Earth itself possessed oceans or continents. The universe is constantly delivering its own history. Yet there is another lesson hidden within these observations. Light accomplishes these journeys effortlessly because it is light. It requires no fuel after it is emitted. It experiences no mechanical wear. It does not need life support, food, oxygen, or shielding from radiation. It simply continues through the vacuum according to the laws of electromagnetism and relativity. Human spacecraft are profoundly different. Every kilogram of equipment demands additional energy. Every scientific instrument adds mass. Every life support system requires power. Every protective shield increases weight. The spacecraft carries not only its destination, but also everything needed to survive the journey. This distinction seems almost trivial while traveling between planets. Within the solar system, it remains manageable. Crossing interstellar distances magnifies every kilogram into an enormous engineering challenge. The farther we wish to travel, the more fuel we require. The more fuel we carry, the heavier the spacecraft becomes. The heavier the spacecraft becomes, the more fuel is needed simply to accelerate the additional fuel already on board. Long before reaching another star, this cycle begins to dominate every design, even before confronting the ultimate limits imposed by physics. Our own methods of transportation struggle under the immense weight of their ambitions. For now, however, those deeper problems remain hidden. At this stage, we've only begun to appreciate the scale of the journey itself. The solar system, immense as it once seemed, is merely a tiny neighborhood surrounding a single ordinary star. To understand why traveling 1 light-year is so daunting, we must first leave that neighborhood behind and discover what truly lies in the vast darkness between the stars. Because what appears empty from a distance turns out to possess a story of its own. The space between the planets already feels immense. A spacecraft leaving Earth quickly discovers that the solar system is not a crowded neighborhood, but an extraordinary expanse of emptiness. Days pass before reaching the moon. Months are required to arrive at Mars when the planets are properly aligned. The outer planets demand journeys measured in years. And beyond Neptune, the Sun itself slowly fades into a bright star among countless others. For generations, this was the edge of the known frontier. When the Voyager spacecraft crossed beyond the orbit of Pluto, they entered a region that had never been visited before. They continued through the Kuiper Belt, a distant realm populated by icy worlds left over from the birth of the solar system. Eventually they approached the heliopause, the invisible boundary where the solar wind, flowing outward from the Sun, begins to yield to the thin gas drifting between the stars. In 2012, Voyager 1 crossed that boundary. It became humanity's first ambassador to interstellar space. The achievement was historic, yet it also carried an unexpected lesson. Despite travelling farther than any previous spacecraft, Voyager had barely begun the journey toward another star. The distance it had covered represented only a tiny fraction of a single light year. The vastness surrounding it remained almost entirely unexplored. This realization forces us to reconsider what we mean by empty space. From Earth's surface, the night sky appears filled with stars. On a clear evening, thousands of points of light decorate the heavens. Photographs taken by powerful telescopes reveal millions more, creating the impression that the universe is densely populated. But appearances can be deceptive. If every star in the night sky were reduced to the size of a grain of sand, the grains would not sit side by side, they would be scattered across continents. The universe is not remarkable because it contains so many stars. It is remarkable because the stars are separated by astonishing distances. Our own Sun drifts through the Milky Way with no neighbouring star close enough to noticeably illuminate the night. Even Proxima Centauri, the closest stellar companion, is so distant that if the Sun suddenly disappeared, its gravitational influence would vanish long before its final light reached that neighbouring system. Space is not merely large, it is overwhelmingly sparse. This emptiness is difficult to appreciate because human intuition evolved in a world where empty regions rarely remain empty for long. Walk across a field, and you encounter trees, rivers, buildings, or mountains. Sail across an ocean, and eventually another coastline appears. Even deserts contain dunes, rocks, and shifting winds that constantly remind travellers of their surroundings. Interstellar space offers something profoundly different. For enormous stretches, there is almost nothing. The average density of the interstellar medium, the thin material filling the galaxy between stars, may be only a few atoms within a volume the size of a cubic centimetre on Earth. That same volume of air contains roughly 20 quintillion molecules. Remove nearly everything, then remove almost everything that remains. The result begins to resemble interstellar space. This extraordinary emptiness creates both opportunity and difficulty. Without air, spacecraft experience no aerodynamic drag, there is no atmosphere to slow them, no friction to wear away their surfaces, and no weather to alter their course. Once accelerated, a spacecraft can continue moving for centuries without needing propulsion simply to maintain its speed. Isaac Newton recognized this principle long before anyone imagined interstellar travel. His first law of motion tells us that an object already in motion remains in motion unless acted upon by an external force. In deep space, there are remarkably few forces available to stop it. At first, this sounds wonderfully encouraging. Launch a spacecraft once, allow it to coast forever. Eventually, surely it must arrive somewhere. The difficulty lies hidden inside one small word. Eventually, if the spacecraft is moving slowly by cosmic standards. Eternity begins to resemble a practical obstacle rather than a philosophical idea. Suppose a probe travelled at 100,000 kilometers per hour. On Earth, such a speed would circle the planet in less than half an hour. It far exceeds the velocity of the commercial aircraft and even surpasses many orbital spacecraft. Across interstellar space, however, it becomes almost insignificant. At that pace, crossing 1 light-year would require more than 10,000 years. A civilization could rise, flourish, fragment, and disappear while its spacecraft remained quietly drifting through the darkness. Time itself becomes part of the journey. This realization has shaped the dreams of astronomers and engineers alike. Throughout history, explorers accepted long voyages because they could reasonably expect to complete them within their own lives. The great ocean expeditions of the 15th century lasted months. Circumnavigating Earth eventually required weeks rather than years. Even voyages to the moon occupied only days. Human exploration has always been measured against the rhythm of a lifetime. Interstellar travel refuses to follow that rhythm, unless a spacecraft can move at an unprecedented fraction of the speed of light. The voyage extends beyond individual experience and enters the timescale of civilizations. The crew, if there is one, may never witness the destination. Their children might not. Perhaps even their distant descendants would remain aboard. Such ideas have inspired concepts known as generation ships, enormous self-sustaining worlds that travel for centuries between the stars. They are fascinating exercises in engineering and sociology, yet even these concepts quietly acknowledge the underlying challenge. They do not make the journey shorter, they merely attempt to make the passage survivable. There is another consequence of interstellar emptiness that is less obvious. Without nearby landmarks, navigation itself becomes surprisingly subtle. Ancient sailors crossed oceans by watching the stars. Future starships may navigate by watching pulsars, rapidly spinning neutron stars whose radio pulses arrive with astonishing regularity. Their predictable rhythms could serve as cosmic lighthouses, allowing spacecraft to determine their position across the galaxy. Even in the deepest darkness, the universe provides reference points, but those reference points also reveal just how vast the distances have become. A star may shine brightly in the night sky while remaining trillions of kilometers away. Brightness, our oldest guide, tells us remarkably little about true distance. Only careful measurement reveals the enormous gaps hidden behind the familiar constellations. By now, one truth has become difficult to ignore. The challenge of travelling 1 light year is not simply that the destination is far away. It is that every ordinary measure of distance, speed, and time begins to lose its meaning once we leave the solar system behind. Yet there remains one deeper reason why these journeys become so difficult. Even if we could build a spacecraft capable of crossing the emptiness between the stars, nature imposes a limit that no traveller has ever surpassed. To understand that limit, we must follow one of the greatest scientific discoveries in history. We must discover why the speed of light is not merely fast, but fundamental for most of human history. Speed seemed to be a wonderfully simple idea. A horse could outrun a person. A ship with a favourable wind could outrun another sailing against the current. Cannonballs travelled faster than arrows, and eventually locomotives surpassed both. Every generation witnessed machines becoming faster than those that came before, encouraging the quiet belief that speed itself had no upper limit. If enough ingenuity could be applied to an engine, why should any velocity remain forever beyond reach? It was a perfectly reasonable assumption. After all, nothing in ordinary life suggested otherwise. If one carriage could travel twice as fast as another, perhaps a better carriage could travel twice as fast again. Improvement appeared to have no obvious boundary. Nature offered resistance through friction and gravity. But these seem like practical obstacles rather than absolute laws. Then, during the 19th century, light began to tell a different story. Light had always occupied a curious place in science. It illuminated the world instantly, or so it seemed. Ancient philosophers debated whether it travelled at all, or whether its presence was immediate. It was not until the 17th century that careful astronomical observations began to reveal something astonishing. Light required time. The Danish astronomer Ole Rømer reached this conclusion while studying the moons of Jupiter. He noticed that one of Jupiter's moons appeared to fall behind schedule whenever Earth was moving away from the giant planet, and appeared ahead of schedule when Earth was moving closer. The moon itself had not changed. The delay belonged to the light carrying the information. For the first time, humanity realized that light possessed a measurable speed. That discovery alone was remarkable. But the deeper surprise would arrive 2 centuries later. As the Industrial Revolution transformed society, scientists increasingly viewed the universe through the language of electricity and magnetism. Among them was the Scottish physicist James Clerk Maxwell, whose elegant equations united electricity, magnetism, and light into a single mathematical framework. His equations produced an unexpected result. They predicted that electromagnetic waves should always travel at one particular speed through empty space, not approximately, not under certain conditions, Always. The number emerged naturally from the mathematics, as though the universe itself had quietly written it into its foundation. Today we know that value to be approximately 299,792 kilometers every second. It is difficult to overstate how strange this prediction seemed. Every other speed people understood depended upon the observer. If you walk forward inside a moving train, your speed relative to the ground is your walking speed plus the speed of the train. The same principle works for bicycles, airplanes, and ships. Why should light behave differently? Physicists naturally assumed that it must. Perhaps light travelled through some invisible substance filling all of space, often called the luminiferous ether. If Earth moved through this invisible medium, then the measured speed of light should change depending on the direction in which it was observed. The idea appeared sensible. It was also testable. In 1887, two American physicists, Albert Michelson and Edward Morley, performed one of the most famous experiments in scientific history. Their instrument was astonishingly precise for its time. Using mirrors and carefully split beams of light, they attempted to detect Earth's motion through the hypothetical ether by measuring tiny differences in the speed of light travelling in different directions. The expected effect was small, but it should have been measurable. Instead, they found nothing. No matter how they rotated their apparatus, no matter what season of the year they observed, the speed of light remained unchanged. It was one of those rare experimental results that solved one mystery while creating a much larger one. If Earth was moving around the Sun at nearly 30 kilometers every second, why did light refuse to acknowledge that motion? For years, physicists struggled to preserve the old picture. Perhaps the ether behaved in unexpected ways. Perhaps the instruments contained subtle errors. Perhaps another explanation remained hidden. Then, in 1905, a young patent clerk in Switzerland proposed something far more radical. Albert Einstein suggested that the experiment was not revealing a flaw in the measurements. It was revealing a flaw in our assumptions. Perhaps the speed of light truly is the same for every observer. Not because space contains a mysterious medium, but because space and time themselves adjust to preserve that constancy. It was an extraordinary idea. At first glance, it seems almost impossible to accept. Suppose two spacecraft pass one another in deep space. Each measures the speed of a beam of light. Common sense suggests that one observer should see the beam moving faster than the other. Einstein's theory predicts otherwise. Both observers measure exactly the same speed, not because either measurement is mistaken, but because their experience of time and distance is subtly different. This was the birth of special relativity. Its consequences remain among the most carefully tested predictions in all of science. Clocks moving at high speed tick more slowly than stationary clocks. Lengths contract along the direction of motion. Mass and energy reveal themselves as different expressions of the same underlying reality. None of these effects are noticeable during everyday life because our ordinary speeds are tiny compared with the speed of light. But as velocities increase, these strange behaviors become impossible to ignore. The closer an object approaches light speed, the more dramatically nature resists further acceleration. This is not because some invisible force suddenly appears. Rather, the relationship between energy, momentum, space, and time changes in ways that Newton's mechanics cannot describe. The equations become increasingly demanding. Every additional increase in speed requires disproportionately more energy. Approaching the speed of light is rather like climbing a mountain whose slope grows steeper with every step. The summit never moves, yet each meter upward demands more effort than the last. Eventually, the required energy becomes so immense that reaching the summit itself remains impossible for any object possessing mass. This is not merely an engineering limitation. It is built directly into our best description of physical reality. Light travels at this extraordinary speed because light consists of particles called photons, which possess no rest mass. Matter is different. Every spacecraft, every astronaut, every atom within your body carries mass. That simple fact changes everything. It means that the challenge of travelling 1 light year is no longer simply a question of building a better engine. The destination remains the same, the distance remains the same, but the closer we attempt to move toward light speed, the more the universe itself begins demanding an almost unimaginable price in energy. And it is that price, measured not only in fuel but in the fundamental laws governing motion, That transforms interstellar travel from an engineering challenge into one of the deepest problems in modern physics. The next step is to discover just how enormous that price truly is. Because once we begin calculating the energy needed to cross even a single light year within a human lifetime, familiar numbers quietly disappear, replaced by scales almost beyond comprehension. By now, the solar system has begun to feel smaller, not because it has changed, but because our perspective has. What once appeared to be the entire stage of cosmic exploration is gradually revealing itself as the front yard of a much larger home. The farther astronomy has looked into the universe, the more one pattern has repeated itself. Every horizon eventually becomes another beginning. Beyond Earth lay the planets. Beyond the planets lay the icy outskirts of the solar system. Beyond the solar system lay the nearest stars. And beyond those stars stretched something even more extraordinary. The Milky Way. On a clear night, far from city lights, the Milky Way appears as a pale ribbon arching across the sky. Ancient civilizations imagined it as a river, a pathway for souls, spilled milk from the gods, or a bridge connecting heaven and earth. Its true nature remained hidden until the invention of the telescope. Even then, understanding arrived slowly. When Galileo Galilei first turned his telescope toward the glowing band in the early 17th century, he discovered that the misty light was not a cloud at all. It was countless individual stars. The realization was breathtaking. The Milky Way was not an object floating among the stars. It was made of stars. Over the centuries, astronomers gradually pieced together a remarkable picture. Our Sun is only one ordinary star among roughly 100 to 400 billion stars orbiting the center of a vast spiral galaxy. Our entire solar system circles that galactic center once every 230 million years, when the dinosaurs walked across Earth. The Sun occupied a completely different region of the Milky Way. Human civilization has existed for only the smallest fraction of a single galactic year. The scales continue to expand. The Milky Way spans approximately 100,000 light-years from one side to the other. Pause for a moment on that number. If crossing 1 light-year already seems almost beyond imagination, then crossing the entire galaxy requires 100,000 times that distance. Even light itself needs 100,000 years to make the journey. The photons leaving one edge of the Milky Way today will not arrive at the opposite side until long after every modern nation. Language and culture has transformed beyond recognition. This is the neighborhood in which our Sun quietly lives. And yet, compared with the observable universe, even our galaxy is only one small island. But before we travel still farther, it is worth lingering here, because the Milky Way teaches an important lesson about distance. The stars scattered across our night sky are not evenly distributed. Some lie only a few light years away, others are hundreds or thousands of light years distant. A bright star is not necessarily nearby. A dim star is not necessarily far away. Brightness depends upon both intrinsic luminosity and distance. The night sky compresses a three-dimensional galaxy into what appears to be a flat dome. It is rather like looking toward a forest from miles away. Two trees may seem to stand side by side. One may actually be only a few meters from you. The other may stand hundreds of meters behind it. From your viewpoint, they overlap perfectly. The stars behave much the same way. Astronomy had to invent ingenious methods to recover this hidden depth. The first reliable technique was stellar parallax. As Earth travels around the Sun during the year, nearby stars appear to shift very slightly against the much more distant background stars. The effect is tiny, even for the nearest stars. The apparent motion is smaller than the width of a coin viewed from several kilometers away. Detecting such movement required instruments of extraordinary precision, yet once astronomers succeeded, the Milky Way suddenly acquired depth. Distances became measurable rather than guessed. The stars were no longer decorations on a celestial sphere. They occupied an immense three-dimensional landscape. Modern spacecraft have transformed this understanding even further. The European Space Agency's Gaia mission has measured the positions, motions, and distances of more than 1 billion stars with astonishing accuracy. Instead of viewing the galaxy as a static collection of lights, astronomers now watch stars orbit, cluster, and drift through space like schools of fish moving through an invisible ocean. The Milky Way is alive with motion. Every star travels Every planetary system journeys through the galaxy. Even our own solar system moves at approximately 220 kilometers every second around the galactic center. Curiously, despite that tremendous speed, we feel nothing. Everything around us shares the same motion. It is another reminder that speed itself is meaningful only relative to something else. Yet even these impressive galactic motions reveal another uncomfortable truth. They are nowhere near the speed of light. Our solar system's rapid orbit around the galaxy amounts to less than 1/10 of 1% of light speed. By cosmic standards, we drift gently. This contrast becomes increasingly important when we consider interstellar travel. Suppose humanity somehow developed a spacecraft capable of traveling 10 times faster than anything we have ever built. It would undoubtedly transform exploration within the solar system. Mars could become weeks away instead of months. The outer planets might be reached within a few years. Missions once considered impossible would become routine. Yet outside the solar system, such an achievement would scarcely change the picture. The nearer stars would still require centuries. The galaxy would remain effectively unreachable. Improving existing technology is not enough. The scales involved are simply too large. This realization has profoundly influenced the search for extraterrestrial intelligence, often known as SETI. If intelligent civilizations exist elsewhere in the Milky Way, why have we not encountered them? One possible answer has little to do with biology or sociology. It may simply be geography. Civilizations could be separated not by hostility or indifference, but by distances so immense that meaningful travel becomes extraordinarily difficult. The galaxy may be full of life. It may also be full of isolation. The stars appear close together only because we view them from unimaginably far away. As our understanding of cosmic scale has grown, another realization has quietly emerged. Distance alone is not the greatest obstacle. If it were, patient engineering might eventually overcome it. The deeper challenge lies in what distance demands. Every additional kilometer requires more energy. Every increase in speed requires still more. Eventually, the relationship stops growing steadily and begins to rise with astonishing intensity. It is here that the mathematics of motion begins to reveal something profoundly humbling. The universe is not merely asking us to build a faster spacecraft. It is asking us to pay an ever-increasing energetic cost for every fraction of light speed we hope to achieve, and that cost grows far faster than intuition would ever suggest. Distance has carried us to the edge of a deeper question. The nearest stars are unimaginably far away. The speed of light appears to be nature's universal limit. The Milky Way stretches across 100,000 light-years. These facts alone make interstellar travel seem daunting. Yet they are not, by themselves, what make the journey so difficult. The true obstacle lies in something far more fundamental: energy. It is an ordinary word, used every day to describe electricity, fuel, batteries, even our own sense of vitality. But in physics, energy is something much more profound. It is the currency through which every change in the universe must be paid. Nothing accelerates without energy. Nothing climbs against gravity without energy. Nothing moves faster than before without paying this invisible cost. For journeys within our own world, the price usually feels manageable. A bicycle requires food. A car requires gasoline. An airplane requires jet fuel. A rocket requires enormous tanks filled with propellant. Each new mode of transportation consumes more energy because it moves faster or carries greater mass. History has accustomed us to this pattern. If a destination is farther away, we simply bring more fuel. That intuition served humanity remarkably well, until we began thinking about the stars. Suppose you wish to send a spacecraft to Proxima Centauri within a human lifetime. Not in 70,000 years, like Voyager. Not in 10,000 years, but perhaps within 20 or 30 years. Immediately, the required speed changes dramatically. Instead of travelling at a few tens of kilometres every second, the spacecraft would need to move at a substantial fraction of the speed of light. That phrase sounds deceptively modest. A substantial fraction. In reality, it means tens of thousands of kilometres every second. No spacecraft has ever approached such velocities. The fastest human-made objects, launched by gravity assists and powerful rockets, travel only a tiny fraction of 1% of light speed. The gap between our current capabilities and interstellar requirements is not like the difference between two generations of aircraft. It is more like the difference between walking across a room and orbiting the Earth. The numbers become difficult to absorb. Physics provides a simple relationship known as kinetic energy for objects moving far below the speed of light. Kinetic energy depends upon two things: mass and the square of velocity. That second detail quietly changes everything. Double your speed. The energy does not merely double, it becomes 4 times greater. Triple the speed, the energy becomes 9 times greater. Increase velocity by a factor of 10. The required energy rises by a factor of 100. This relationship is gentle at everyday speeds. It becomes overwhelming as velocities climb. Imagine pushing a child on a swing. The first few pushes are easy. Each additional push sends the swing a little higher. Now imagine that. Instead of becoming slightly harder each time, every push required twice the effort of the previous one. Soon, no human strength would be sufficient. Acceleration toward light speed behaves in a similar way. The closer you come, the more expensive every additional increase becomes. And this is before relativity introduces its own even steeper demands. For ordinary speeds, Newton's equations work beautifully. But once velocities become a significant fraction of the speed of light, Einstein's equations take over. The energy required no longer follows the familiar pattern alone. It begins rising faster and faster. As an object approaches light speed, the required energy grows without bound. The mathematics does not predict a very difficult engineering challenge. It predicts an impossible one. No finite amount of energy can accelerate an object with mass to exactly the speed of light. This conclusion has survived more than a century of experimental testing. Particle accelerators routinely push electrons and protons to astonishing velocities. Some particles reach more than 99.99999% of the speed of light. Yet despite enormous increases in energy, they never quite reach light speed. Every additional fraction becomes harder to obtain than the last. Nature appears perfectly consistent. The limit remains intact. There is another complication. A spacecraft does not travel alone. It carries itself. This sounds almost trivial, but it creates one of the greatest engineering difficulties ever encountered. Suppose you wish to accelerate a spacecraft. You need fuel, but that fuel has mass. Therefore, accelerating the fuel also requires energy. If you bring additional fuel to accelerate the original fuel, that new fuel must itself be accelerated. The cycle repeats. The 19th century Russian scientist Konstantin Tsiolkovsky recognized this problem long before spaceflight became reality. His famous rocket equation revealed an uncomfortable truth. As mission requirements increase, the amount of propellant grows exponentially. A slightly faster mission may require dramatically more fuel. A much faster mission may require absurdly more. Eventually, the rocket becomes almost entirely fuel, carrying only a tiny useful payload. This is why modern launch vehicles appear so enormous. The astronauts, satellites, or scientific probes occupy only a small portion near the top. Most of the rocket consists of propellant needed simply to lift the propellant beneath it. Even escaping Earth's gravity demands this extraordinary arrangement. Interstellar travel magnifies the challenge many thousands of times. Chemical rockets, magnificent as they are, simply cannot provide enough energy. The chemical bonds inside gasoline or liquid hydrogen release impressive amounts of energy by everyday standards. Compared with what interstellar travel demands, however, they're astonishingly weak. It is rather like attempting to cross an ocean in a sailboat powered by a single candle. The flame is real. It simply cannot produce enough work. This realization explains why scientists rarely discuss chemical propulsion when considering journeys between the stars. The conversation quickly shifts toward nuclear fusion, antimatter, laser propulsion, concepts that sound almost futuristic. Not because researchers enjoy exotic ideas, because the familiar alternatives fail by enormous margins. Even the sun itself offers perspective. Every second, our star converts roughly 4 million tons of matter into energy through nuclear fusion. The resulting power sustains every ecosystem on Earth and illuminates the solar system. Yet despite producing this unimaginable output continuously for billions of years, the sun does not propel itself through the galaxy at anything close to light speed. Stars possess extraordinary energy. They also possess extraordinary mass. The balance between the two reminds us how demanding relativistic motion truly is. Perhaps the most humbling realization is this. Humanity has never lacked imagination. Across history, every impossible journey eventually inspired a new invention. The wheel, the compass, steam engines, aircraft, rockets. Interstellar travel inspires the same optimism. But unlike previous frontiers, the stars confront us with a challenge that cannot be solved simply by building a larger engine or carrying a larger fuel tank. The difficulty originates not in our machines. It originates in the very relationship between mass, energy, and motion that governs the universe itself. Yet physics rarely presents only obstacles. Every limitation also reveals where new possibilities might exist. If conventional rockets demand impossible amounts of fuel, perhaps the answer is to stop carrying fuel altogether. If chemical energy is insufficient, perhaps entirely different sources of energy must be considered. Some of the most creative scientific ideas ever proposed begin precisely at this point. They ask not how to improve today's rockets, but how to rethink propulsion from the ground up. And in searching for those possibilities, scientists have uncovered solutions that are as elegant as they are extraordinary. Whether any of them will truly carry humanity to another star remains one of the most fascinating questions in modern astronomy. Every great engineering challenge begins with a single obstacle. Build a bridge strong enough to cross a river. Design an aircraft powerful enough to leave the ground. Construct a rocket capable of escaping Earth's gravity. The problem may be difficult, but it has a clear center. Solve the primary challenge, and many of the smaller ones begin to fall into place. Interstellar travel refuses to behave this way. Every solution creates another problem. Every answer reveals a new question. It is less like climbing a mountain than walking through a labyrinth where every doorway opens into another corridor. By now, we know that energy is the first barrier. Reaching even a modest fraction of the speed of light demands an extraordinary amount of it. But suppose, for a moment, that humanity somehow solved this problem. Suppose an engine existed that could provide exactly the energy we needed. The journey would still be far from possible, because acceleration is only the beginning. Eventually, every spacecraft must slow down. This detail is surprisingly easy to overlook. When we picture a voyage to another star, our attention naturally focuses on departure. We imagine the engines igniting, the spacecraft pulling away from the solar system, and the long journey through interstellar darkness. But a spacecraft that never decelerates does not arrive. It merely passes by at 20% of the speed of light. Even an entire planetary system becomes a fleeting destination. The distance from Earth to the Moon would be crossed in little more than 6 seconds. A planet orbiting another star would appear and disappear before astronauts had time to observe it closely. A successful interstellar mission requires 2 journeys, one to accelerate, one to stop. That simple requirement nearly doubles the energy problem. It also complicates spacecraft design. Should fuel for deceleration be carried from Earth? If so, the spacecraft becomes heavier. A heavier spacecraft requires more energy to accelerate. That additional energy demands more fuel, which increases the mass once again. The familiar cycle quietly returns. Some proposed missions attempt to avoid this trap by using external sources of energy. Perhaps giant lasers near Earth could push a spacecraft outward using light itself. Perhaps magnetic fields surrounding another star could help slow it down. Perhaps an advanced civilization could construct infrastructure extending far beyond its home system. Each idea addresses one difficulty. None eliminates them all. Then there is the question of time. Not simply travel time. Human time. Every spacecraft carrying people must also carry a small, self-contained world. Air must remain breathable. Water must remain clean. Food must be produced or preserved. Machines must continue operating for decades. Medical care must remain available. Psychological health must be maintained despite extraordinary isolation. A mission lasting 30 years asks far more than whether an engine can continue functioning. It asks whether an entire civilization, compressed into the volume of a spacecraft, can remain healthy for a generation. The International Space Station has provided valuable insight into living away from Earth. Astronauts spend months in orbit. They experience muscle loss despite daily exercise. Bone density decreases. Radiation exposure increases. Even with constant communication and regular supply missions, life in space remains demanding. An interstellar spacecraft would have none of those advantages. There would be no cargo ship arriving with spare parts. no possibility of returning home after an emergency, no nearby planet capable of supporting life. The spacecraft itself would become the only home its inhabitants would ever know, and unlike Earth's ecosystems, every resource would have to be recycled with extraordinary efficiency. Nothing could be wasted. Every drop of water, every gram of oxygen, every kilogram of material. The margin for error would be remarkably small. Radiation introduces another layer of complexity. Earth is protected by two remarkable shields. The first is its magnetic field, which deflects many charged particles arriving from the sun and deep space. The second is its atmosphere, which absorbs much of the remaining high-energy radiation before it reaches the surface. Together, they create an environment where complex life can flourish. Deep space offers no such protection. Cosmic rays travel through the galaxy at enormous energies. Many originate from exploding stars called supernovae. Others may come from even more energetic events surrounding black holes or distant galaxies. Unlike ordinary sunlight, these particles can pass through spacecraft walls, damaging electronics and living tissue alike. Over months or years, the accumulated exposure becomes a serious concern. Shielding seems like the obvious answer. Simply build thicker walls. But thicker walls increase mass. Greater mass requires more energy. More energy demands more fuel. The chain appears once again. Even communication becomes unexpectedly difficult. Signals cannot travel faster than light. A message sent from Earth to Proxima Centauri requires more than 4 years to arrive. A reply requires another 4. An ordinary conversation stretches across nearly a decade. Mission control, as we understand it today, becomes impossible. Every decision must be made locally. The spacecraft must operate with extraordinary autonomy. Artificial intelligence may eventually assist such missions, but autonomy introduces its own questions. How should an intelligent system respond to unforeseen emergencies? What happens if it fails after 20 years? Who repairs the system responsible for repairing every other system? Every answer creates another dependency. Navigation follows the same pattern. A tiny error in direction, almost impossible to notice near Earth, grows steadily over trillions of kilometers. A deviation of only a fraction of a degree can eventually place the spacecraft billions of kilometers away from its intended destination. Tiny imperfections become enormous consequences. Astronomers often compare interstellar travel to threading a needle from thousands of kilometers away. Precision becomes inseparable from patience. Then comes perhaps the most subtle challenge of all: reliability. Modern spacecraft are astonishingly dependable. Voyager 1 has continued operating for nearly half a century. Some Mars rovers survived years beyond their planned lifetimes. These achievements are extraordinary. Yet they also reveal the scale of the problem. A voyage lasting 40 or 50 years requires machines expected to function longer than many engineers' entire careers. Some components would inevitably fail. Lubricants slowly degrade. Materials become brittle. Electronics age. Even tiny manufacturing imperfections can eventually become mission-ending failures. Designing a spacecraft for interstellar travel is therefore unlike designing almost anything humanity has built before. It must not merely survive launch. It must survive decades of continuous operation in one of the harshest environments known. Each individual challenge seems manageable when viewed alone. Energy, fuel, radiation, life support, navigation, communication, reliability, but they cannot be solved independently. Every improvement in one area often creates new demands elsewhere. Heavier shielding increases fuel requirements. Additional fuel increases mass. Greater mass demands stronger structures. Stronger structures require more material. More material again increases mass. The spacecraft becomes an intricate web of compromises. Engineers sometimes describe this kind of problem as tightly coupled. No single decision exists in isolation. Interstellar travel may be the most tightly coupled engineering challenge humanity has ever contemplated. And yet, despite this remarkable complexity, scientists have never stopped searching for solutions. Some are grounded in technologies already under development. Others depend upon physics that has yet to mature into engineering. Together, they represent perhaps the boldest collection of ideas ever proposed for exploring the cosmos. The question is no longer whether conventional rockets can reach another star. We already know their limitations. The question becomes whether entirely different methods of propulsion can persuade the universe to reveal a more practical path. Every age has imagined a vehicle that could carry humanity farther than ever before. The age of sail produced ships capable of crossing oceans once believed impassable. The Industrial Revolution gave birth to railways that shrank continents. The 20th century transformed flight from a fragile experiment into a routine journey and carried astronauts beyond Earth's atmosphere. Each breakthrough shared a common characteristic. It was built upon technologies that already existed in simpler forms. Interstellar travel offers no such gradual path. The engines capable of reaching another star have never been built. Some may eventually become reality. Others may remain beautiful ideas written only in equations. Modern astronomy and physics therefore distinguish carefully between engineering proposals, theoretical possibilities, and concepts that remain entirely speculative. This distinction matters, because while imagination can travel anywhere, science advances only where evidence allows. The most familiar proposal begins with nuclear energy. Chemical rockets derive their power from rearranging the electrons surrounding atoms. Nuclear reactions reach much deeper. They alter the atomic nuclei themselves, releasing vastly greater amounts of energy. This difference is enormous. A small amount of nuclear fuel contains millions of times more usable energy than an equal mass of chemical propellant. That is why the sun shines for billions of years. Its energy comes not from burning in the ordinary sense, but from nuclear fusion. Fusion joins light atomic nuclei together, converting a tiny fraction of their mass directly into energy. According to Einstein's famous equation, mass and energy are interchangeable. Even a very small loss of mass produces an extraordinary amount of energy. For decades, engineers have wondered whether a fusion-powered spacecraft could someday carry humanity toward the stars. On paper, the concept is compelling. A fusion engine could operate continuously for months or even years, slowly accelerating until reaching velocities far beyond those possible with chemical rockets. Unlike conventional engines, it would not rely upon explosive bursts of combustion. Instead, it would gently but persistently build speed across enormous distances. Several serious research studies have explored this possibility. One of the most famous was Project Daedalus, designed during the 1970s by members of the British Interplanetary Society. It was never intended to be constructed with the technology of its time. Instead, it asked a simple question. If physics places no fundamental prohibition on fusion propulsion, what might such a spacecraft actually look like? The answer was astonishing. The proposed vehicle would dwarf anything humanity has ever launched. Its fuel alone would weigh tens of thousands of tons. Even with fusion, extraordinary quantities of propellant remain necessary. The study reached an encouraging conclusion, and a sobering one simultaneously. Interstellar travel might be physically possible. It would also demand engineering on a scale civilization has never attempted. Fusion itself presents another challenge. Scientists have pursued controlled nuclear fusion for decades. Experimental reactors continue making remarkable progress. Yet producing more energy than the reactor consumes remains one of the most demanding problems in modern engineering. Before fusion can propel spacecraft, it must first become a practical source of power here on Earth. If fusion appears ambitious, antimatter seems almost mythical. Every ordinary particle has an antimatter counterpart. An electron possesses a positively charged partner called the positron. Protons possess antiprotons. When matter and antimatter meet, they annihilate each other. Almost all of their mass becomes energy. No known process converts matter into usable energy more efficiently. For this reason, antimatter is often described as the ultimate rocket fuel. A remarkably small quantity could release energy comparable to enormous amounts of conventional propellant. In theory, an antimatter engine could propel spacecraft to unprecedented speeds. In practice, however, antimatter presents difficulties almost beyond imagination. Producing even microscopic quantities requires particle accelerators consuming vast amounts of electricity. The cost of manufacturing appreciable amounts would be astronomical by today's standards. More challenging still, antimatter cannot touch ordinary matter. The moment it does, both disappear in a burst of energy. It must therefore be suspended inside magnetic fields, never contacting the walls of its container. Designing storage systems capable of safely containing significant quantities for years or decades remains entirely beyond present technology. Antimatter is not forbidden by physics. It is simply astonishingly difficult to produce, contain, and use. Another family of ideas abandons the traditional rocket altogether. Perhaps the spacecraft should not carry its own energy. Instead, the energy could remain at home. Light itself carries momentum. Normally the effect is extraordinarily small. Sunlight gently pushes on every object it strikes. The force is so weak that it goes unnoticed in daily life. Yet in the vacuum of space, where no friction exists, even a tiny continuous push gradually builds speed. This principle has already been demonstrated. Several spacecraft have successfully deployed solar sails, enormous reflective sheets that use sunlight as propulsion. The acceleration is gentle, but it is continuous. Over months and years, meaningful velocities become possible. Researchers have proposed extending this idea dramatically, instead of relying upon sunlight alone. Immense arrays of powerful lasers could direct concentrated beams toward an ultralight spacecraft equipped with a reflective sail. The photons themselves would provide the thrust. The spacecraft would carry almost no fuel. Projects such as Breakthrough Starshot explore versions of this concept. Their goal is extraordinarily ambitious. Send tiny robotic probes toward Proxima Centauri at perhaps 20% of the speed of light. At such velocities, the journey could require only a few decades. The proposal rests upon known physics. Photons truly possess momentum. Laser beams truly exert pressure. The uncertainty lies in engineering. Can humanity build laser arrays powerful enough? Can sails survive such intense illumination? Can miniature spacecraft remain operational after decades in interstellar space? These questions remain open. Then there are concepts that blur the boundary between engineering and theoretical physics. One proposal involves collecting the sparse hydrogen atoms drifting through interstellar space and using them as fusion fuel during flight. Known as the Bussard ramjet, it would eliminate the need to carry enormous quantities of propellant from Earth. The idea is elegant. Unfortunately, detailed calculations suggest the interstellar medium may be far too thin to provide sufficient fuel, and the collection mechanism itself could generate more drag than thrust. Whether the concept can ever be made practical remains uncertain. Finally, we reach ideas that have captured the public imagination perhaps more than any others. Warp drives. Unlike rockets, warp drives do not attempt to move a spacecraft through space at extraordinary speed. Instead, they seek to alter space itself. General relativity allows space-time to stretch, bend, and expand. Indeed, the universe itself has been expanding since the Big Bang. In 1994, physicist Miguel Alcubierre proposed a mathematical solution, suggesting that a region of compressed space ahead of a spacecraft and expanded space behind it might effectively allow faster-than-light travel without locally violating relativity. It was a fascinating result. It was also deeply speculative. The equations require forms of negative energy or exotic matter that have never been observed in the necessary quantities. Whether such materials can exist at all remains unknown. Warp drives therefore occupy a very different category from fusion engines or laser sails. They are not established engineering projects. They are mathematical possibilities whose physical reality remains uncertain. This distinction is essential. Science advances by carefully separating what has been demonstrated from what has merely been imagined. Some concepts discussed in this chapter are supported by laboratory experiments. Some are supported by well-tested physical theory. Others await discoveries that may or may not ever occur. The stars do not become closer simply because our ideas become more creative. Yet each proposal teaches us something valuable. Every serious attempt to solve interstellar travel illuminates another aspect of the universe's laws. Some reveal unexpected opportunities. Others reveal hidden limitations. And together they prepare us for one of the strangest consequences of approaching the speed of light. For if one of these extraordinary engines were ever built, the journey would not simply change where we travel, it would change how time itself unfolds for the travelers making the voyage. The closer a spacecraft moves toward the speed of light, the stranger the journey becomes. Up to this point, every obstacle we have explored has seemed familiar in principle. Greater distances require more travel time. Higher speeds demand more energy. Larger spacecraft need more fuel. These ideas are intuitive. They belong to the world of everyday experience. Relativity does not. It asks us to leave behind some of our deepest assumptions about reality itself. Most people think of time as something universal. A clock on Earth ticks 1 second after another. A clock aboard a spacecraft does the same, if two identical clocks begin together. Common sense suggests they should always agree unless one is broken. Nature quietly disagrees. One of the most remarkable discoveries of modern physics is that time is not the same for everyone. It depends upon motion. The effect is extraordinarily small during ordinary life. A commercial airliner flies far too slowly for passengers to notice anything unusual. Even astronauts orbiting Earth experience only tiny differences, yet those tiny differences are real. Highly accurate atomic clocks carried aboard aircraft have confirmed them. Satellites orbiting Earth must account for relativistic effects every single day. Without these corrections, the global positioning system would gradually become inaccurate by several kilometers. Relativity is not an abstract curiosity. It quietly helps people navigate highways, oceans, and cities every day. But the phenomenon becomes truly astonishing only when speed approaches that of light. Suppose a spacecraft somehow reaches 90% of light speed. From the perspective of observers on Earth, the voyage proceeds exactly as expected. The spacecraft races away through the darkness. Years pass, stars slowly grow brighter ahead of it. Nothing appears especially mysterious. Now consider the experience aboard the spacecraft itself. The crew's clocks continue ticking normally. Their hearts beat at familiar rhythms. Meals are eaten. Conversations unfold. Nothing about daily life seems unusual. Yet when they eventually compare their clocks with those left behind on Earth, something extraordinary has happened. Less time has passed for the travelers. This effect is known as time dilation. It has been measured repeatedly in laboratories and particle accelerators. Particles moving close to light speed survive longer than identical particles at rest because, from our perspective, their internal clocks are running more slowly. Nature performs this experiment millions of times every day. High-energy particles called muons are constantly created in Earth's upper atmosphere by cosmic rays. At rest, muons decay in only a tiny fraction of a second. Without relativity, very few should ever reach the ground. Yet many do. Their tremendous speed slows the passage of their own time relative to Earth, allowing them to survive the journey. The mathematics predicts precisely what experiments observe. This is no longer a controversial idea. It is among the most thoroughly verified consequences of special relativity. The implications for interstellar travel are profound. Imagine a spacecraft capable of sustaining 99% of the speed of light. From Earth's perspective, reaching a star 100 light-years away would require slightly more than 100 years. No one who launched the mission would live to welcome its arrival. For the astronauts, however, far less time would pass. Their journey might occupy only years or decades, depending upon the exact speed and periods of acceleration. The destination itself has not moved closer. Time has unfolded differently. At first glance, this seems almost miraculous. Could relativity solve the problem of interstellar travel after all? The answer is both yes and no. Yes, because the travelers themselves might experience surprisingly manageable journey times. No, because everyone waiting for them does not. Time dilation does not shorten history. It merely distributes time differently between observers. Suppose a crew leaves Earth on an extraordinarily fast mission. They return after what feels like 20 years aboard their spacecraft. Upon landing, they discover that centuries have passed on Earth. Languages have changed. Cities have disappeared. New civilizations may have risen where familiar nations once stood. Every friend and family member has long since vanished into history. The voyage becomes not merely a journey through space. It becomes a journey into Earth's future. Science fiction has explored this idea for generations. Modern physics recognizes it as a natural consequence of special relativity. There is no contradiction. Every observer measures time correctly according to their own motion. The universe simply refuses to provide one universal clock shared equally by everyone. Another remarkable effect accompanies time dilation. As speed increases, distances measured in the direction of travel become shorter for the moving observer. This phenomenon is known as length contraction. Again, it sounds impossible. Surely the distance between stars cannot actually change. From Earth's perspective, it does not. Proxima Centauri remains approximately 4.24 light-years away. The Milky Way remains about 100,000 light-years across. Yet aboard a spacecraft travelling at relativistic speed, those distances appear compressed. not because the galaxy physically shrinks, but because space and time are woven together into space-time. Changing one inevitably influences the other. This is perhaps the most difficult idea in the entire documentary. Our intuition insists that space is fixed and time flows independently. Einstein revealed that neither assumption survives careful measurement. The faster you move, the more your measurements of distance and time differ from those made by someone moving differently. Both descriptions are correct. Neither observer is privileged. The laws of physics remain identical for both. One way to appreciate this is to think about a map. A flat paper map can represent Earth's curved surface, but every projection introduces distortions. Some preserve direction, others preserve area. None preserve everything simultaneously. Space-time behaves somewhat similarly. Different observers moving relative to one another make different measurements, yet all remain consistent within the underlying geometry described by relativity. The universe is not contradicting itself. It is simply richer than ordinary experience suggests. This realization has inspired both excitement and misunderstanding. Occasionally, one hears claims that relativity allows unlimited faster-than-light travel. It does not. Time dilation and length contraction occur precisely because nothing with mass crosses the speed of light. The closer a spacecraft comes to that limit, the stronger these effects become. They are consequences of the limit, not exceptions to it. In fact, they reinforce the remarkable consistency of Einstein's theory. Every strange phenomenon emerges naturally from the same mathematical framework that predicts the constant speed of light. Nothing needs to be added. Nothing needs to be adjusted. The pieces fit together with extraordinary elegance. Still, even if future technology carried astronauts across dozens of light years within their own lifetimes, another sobering truth remains. The galaxy itself would continue evolving while they travelled. Civilizations would rise and fall. Stars would continue orbiting the Milky Way. History would unfold at home while the travellers experienced only a small fraction of that passing time. Interstellar exploration, therefore, is not simply about crossing distance. It is about accepting that different journeys may also carry different histories. And yet, despite the extraordinary beauty of relativity, there remains a danger that no equation about time can eliminate. The faster a spacecraft travels, the more threatening even the smallest particle drifting through interstellar space becomes. The emptiness between the stars, which once seemed reassuring, begins to reveal a hidden violence of its own. At first, the Milky Way appears to offer comfort. Once we understand that time flows differently for travellers moving close to the speed of light, interstellar journeys seem just a little less impossible. A crew might cross dozens of light years while aging only a few decades. The mathematics of relativity appears to grant a remarkable gift, but the galaxy quietly reminds us that even extraordinary gifts have limits. The Milky Way is simply too large. Our Sun resides about 26,000 light-years from the galactic centre, orbiting within one of the galaxy's spiral arms. It is neither especially close to the centre, nor particularly near the edge. It occupies an ordinary location among hundreds of billions of stars. This ordinary location is itself extraordinary, because wherever one stands inside the Milky Way, the same lesson emerges. The galaxy refuses to become small. Suppose humanity someday develops a spacecraft capable of reaching 10% of the speed of light. Such a breakthrough would eclipse every previous achievement in transportation. Voyages to the nearest stars would require only a few decades. Nearby planetary systems could eventually be explored. Within the solar system, distances would seem almost insignificant. Mars might become a destination measured in days, Jupiter in weeks, the outermost planets in months. Our own stellar neighbourhood would begin to resemble the great age of ocean exploration on Earth. Yet the wider galaxy would remain astonishingly distant, at 10% of a light speed. Crossing the Milky Way would still require roughly 1 million years from Earth's perspective. Even if the travellers experienced somewhat less time because of relativistic effects, the journey would still unfold across timescales that dwarf the existence of civilizations. This realization changes how we think about the universe. We often describe galaxies as collections of stars. That is true, but another description is equally accurate. Galaxies are collections of enormous separations. Their defining feature is not merely the number of stars they contain. It is the immense emptiness between those stars. Our intuition struggles with this because photographs compress the galaxy into a single image. Seen from afar, the Milky Way resembles a graceful spiral of glowing light. The spiral arms appear continuous, almost solid. In reality, they are astonishingly diffuse. If our sun were reduced to the size of a grain of sand, the nearest star would still lie several kilometers away. The galaxy is beautiful precisely because it is so sparse. Even the densest stellar regions contain far more emptiness than matter. This immense spacing creates an unexpected consequence. Travel between neighbouring stars is already an extraordinary undertaking. Travel between opposite sides of the galaxy becomes something almost unimaginable. Even communication slows to a crawl. A message sent from one side of the Milky Way to the other requires approximately 100,000 years to arrive. Consider what that means. A civilization transmitting a greeting today would not receive a reply until 200,000 years had passed. By then, continents on Earth would have changed. Entire species might have appeared or vanished. Human civilization itself has existed for only a tiny fraction of that interval. The speed of light, so unimaginably fast within the solar system, becomes surprisingly slow across a galaxy. This has led astronomers to ask an intriguing question. If intelligent civilizations exist elsewhere in the Milky Way, how would they experience the galaxy? Perhaps not as a single connected society, perhaps instead as countless isolated islands. On Earth, oceans once separated civilizations for centuries. Ideas travelled slowly. Cultures developed independently. Only with improvements in transportation and communication did the world gradually become interconnected. The Milky Way may never undergo such a transformation. Even civilizations possessing technologies far beyond our own would remain constrained by relativity. Messages could not outrun light. Journeys would still demand immense investments of time and energy. Distance would continue shaping history. This perspective offers one possible answer to a famous scientific puzzle known as the Fermi paradox. If the galaxy contains so many stars, and many of those stars possess planets, why have we not encountered evidence of advanced civilizations? Many explanations have been proposed. Perhaps intelligent life is exceedingly rare. Perhaps civilizations destroy themselves before mastering interstellar travel. Perhaps they deliberately remain silent. Or perhaps the answer is much simpler. The galaxy itself is extraordinarily difficult to cross. A civilization may flourish for millions of years while never expanding beyond a modest region surrounding its home star. The Milky Way could host many isolated cultures, each separated by distances that make meaningful interaction extraordinarily difficult. This possibility requires no exotic physics, only patience and scale. Astronomers have discovered that stars themselves are not stationary. Every star follows its own orbit around the galaxy. Some move faster, some slower. Some drift gradually away from one another. Others pass surprisingly close over millions of years. The galaxy resembles a vast dance whose choreography unfolds almost too slowly for human perception. This motion subtly alters the map of future exploration. Proxima Centauri is our nearest stellar neighbour today. It will not always remain so. Over hundreds of thousands of years, neighbouring stars slowly exchange positions. Future civilizations may inherit a different collection of nearby destinations than we do. The Milky Way is not frozen, it evolves continuously. This evolution becomes even more dramatic on larger timescales. Spiral arms rotate, star clusters disperse. New stars are born inside immense clouds of gas. Old stars exhaust their nuclear fuel and quietly fade into white dwarfs, collapse into neutron stars, or become black holes. The galaxy we see tonight is only one moment in an ongoing story. If humanity someday embarks upon voyages lasting thousands or tens of thousands of years, those travellers will not simply witness different places, they will witness a different galaxy. The night sky surrounding their destination may bear little resemblance to the one they left behind. Constellations, familiar only because of our present location and era, will slowly dissolve. The stars themselves redraw the heavens. There is something quietly humbling about this realization. We often think of ourselves as moving through space while the universe remains still. In truth, everything is moving. Earth circles the sun circles the Milky Way. The Milky Way itself moves among neighbouring galaxies. Even the galaxies participate in the expansion of the universe. Stillness is largely an illusion created by our limited perspective. Yet despite all this motion, one truth remains stubbornly unchanged. The distances are immense. The energy demands remain extraordinary. The speed of light continues to govern every journey. And even if every engineering problem discussed so far were somehow overcome, another obstacle waits silently in the darkness between the stars. It is almost invisible, a lone atom, a microscopic grain of dust, a tiny fragment of matter drifting unnoticed through interstellar space. At ordinary speeds, such particles are harmless. At relativistic speeds, they become something entirely different. The emptiness between the stars is not as empty as it first appeared, and the faster a spacecraft travels, the more dangerous that almost invisible emptiness becomes. There is a comforting image that often accompanies discussions of space. A spacecraft glides silently through an endless black ocean. Nothing surrounds it except distant stars. The vacuum appears perfectly empty, perfectly still, offering an unobstructed path toward another sun. It is a beautiful picture. It is also incomplete. Interstellar space is astonishingly empty compared with anything we experience on Earth. Yet astonishingly empty is not the same as truly empty. Between the stars drifts an invisible population of atoms, molecules, microscopic dust grains, magnetic fields, and high-energy particles. Individually, they seem insignificant. Collectively, they become one of the greatest challenges facing any spacecraft that attempts to travel at relativistic speeds. The danger is not their size, it is the speed of the encounter. Anyone who has driven a car has experienced the surprising force of a tiny raindrop striking the windshield. At walking speed, rain feels gentle. At highway speed, the same droplets strike with noticeable force. The raindrop has not changed, only the relative velocity has. Now extend that idea far beyond ordinary experience. A grain of dust no larger than a speck of smoke drifts quietly through interstellar space. It may have wandered there for millions of years, moving peacefully around the Milky Way with little consequence. A spacecraft travelling at 20% of the speed of light suddenly encounters it. The dust grain has become a projectile, not because it accelerated, but because the spacecraft did. Physics has no preference for which object is considered to be moving. Only the relative speed matters. At such velocities, even microscopic particles carry extraordinary kinetic energy. An impact that would be completely harmless at ordinary speeds can release energy comparable to a powerful explosive. Researchers studying relativistic spacecraft have performed detailed calculations of these collisions. Their conclusions are remarkably consistent. The greatest threat may not come from large asteroids, which are relatively rare and easier to detect. Instead, it comes from countless tiny particles that are almost impossible to see before impact. A single grain only fractions of a millimeter across could severely damage an unprotected spacecraft traveling at a significant fraction of light speed. This realization changes the design philosophy entirely. Instead of asking only how to accelerate a spacecraft, engineers must also ask how to protect it throughout decades of travel. One obvious solution is shielding. Build a stronger spacecraft. Construct thicker walls. Use tougher materials. The idea sounds straightforward. Until mass enters the conversation once again, every kilogram of protective shielding increases the spacecraft's weight. Additional weight demands additional energy. Additional energy requires additional propulsion. The familiar chain quietly returns. The same compromise appears yet again. Scientists have therefore explored more creative approaches. Some proposed spacecraft designs place a large sacrificial shield far ahead of the main vehicle. The shield absorbs incoming impacts while protecting the crew and delicate equipment behind it. Others suggest clouds of tiny particles could be released ahead of the spacecraft, colliding with incoming dust before it reaches the hull. Still others investigate magnetic or plasma shields capable of deflecting charged particles. Each approach offers advantages. Each introduces new engineering challenges. Charged particles create a different kind of hazard. Throughout the Milky Way, energetic atomic nuclei constantly race through space at nearly the speed of light. These are cosmic rays. Unlike ordinary sunlight, cosmic rays possess enormous energies. Some originate when massive stars explode as supernovae. Others appear to come from environments surrounding neutron stars or black holes. A few possess energies so extreme that astronomers are still uncertain exactly where they originate. When these particles strike biological tissue, they can damage DNA. When they strike electronic systems, they may flip individual bits of information inside computer memory or gradually degrade sensitive components. On Earth, we rarely think about such dangers because our planet quietly protects us. Our magnetic field deflects many incoming charged particles. Our atmosphere absorbs many of the rest. By the time sunlight reaches the ground, most of its harmful radiation has already been filtered away. Deep space provides no comparable shelter. The farther a spacecraft travels from Earth, the more it must depend upon its own protection. This challenge becomes particularly serious during journeys lasting decades. Radiation damage is cumulative. A single particle may do very little. Millions or billions of particles over many years tell a different story. Human biology evolved beneath Earth's protective envelope. Interstellar space asks it to survive in an environment for which evolution never prepared it. Modern spacecraft already experience smaller versions of these problems. Satellites occasionally suffer what engineers call single-event upsets. A single energetic particle passes through a computer chip, altering stored information. Most errors are corrected automatically. Occasionally they cause more serious malfunctions. Engineers devote enormous effort to designing electronics capable of surviving the harsh radiation environment surrounding Earth. Interstellar missions would demand an even greater level of resilience. Yet perhaps the most surprising hazard comes not from radiation or dust alone. It comes from hydrogen. Hydrogen is the most abundant element in the universe. Interstellar space contains vast numbers of individual hydrogen atoms drifting between the stars. Normally, they are so sparse that they seem almost irrelevant. At relativistic speeds, they become something else. From the spacecraft's perspective, those quiet atoms arrive carrying enormous energies. The forward-facing surface of the spacecraft effectively experiences a continuous stream of high-energy impacts. The faster the spacecraft travels, the more intense this invisible bombardment becomes. It is almost as though empty space gradually transforms into a powerful wind, not because space itself changes, but because motion changes the nature of every encounter. This subtle idea reveals something profound. Speed reshapes reality. The same environment experienced by a slow-moving spacecraft becomes fundamentally different for one approaching light speed. A region that appears almost perfectly empty to Voyager becomes an energetic obstacle course for a relativistic starship. Perspective matters. Velocity matters. Relativity quietly influences not only time and distance, but the practical experience of moving through the cosmos. Astronomers have learned similar lessons while observing nature itself. Neutron stars, among the densest objects in the universe, generate winds of particles moving at extraordinary speeds. Black holes accelerate matter into narrow jets that extend thousands of light years. Supernova explosions hurl material across interstellar space at velocities unimaginable on Earth. The universe has already demonstrated what happens when matter approaches extreme energies. Violence emerges naturally. Human spacecraft attempting comparable speeds would encounter gentler versions of these same physical principles. Fortunately, the story is not entirely one of danger. Every challenge discussed so far has also inspired new scientific understanding. Research into radiation shielding improves spacecraft designed for Mars. Studies of cosmic dust deepen our understanding of how planets form. Investigations into advanced materials produce technologies with applications far beyond astronomy, even if humanity never crosses 1 light year. The attempt itself continues expanding scientific knowledge. Perhaps this has always been the deeper pattern of exploration. Every frontier teaches us something before it allows us to cross. Sometimes the lesson is geographical, sometimes technological, sometimes philosophical. Interstellar space seems determined to teach all three at once. And today, we possess tools that previous generations could scarcely have imagined for learning those lessons. Powerful space telescopes peer into distant stellar nurseries. Spacecraft sample asteroids and comets. Computer simulations recreate the birth of galaxies and the evolution of stars without leaving our own solar system. Modern astronomy is gradually uncovering the secrets of the very journeys we hope one day to undertake. The remarkable story of those discoveries is only beginning. Long before humanity possesses a spacecraft capable of crossing 1 light year, we have already begun preparing for the journey, not by building an interstellar vessel, but by learning how the universe truly works. One of the quiet strengths of modern astronomy is that it rarely waits for the perfect technology before asking profound questions. Instead, each new telescope, spacecraft, and computer simulation becomes another small step toward understanding a destination we may not reach for centuries. In that sense, interstellar exploration has already begun. It simply began with observation rather than travel. Every night, observatories around the world collect light that has crossed enormous distances. Some photons began their journeys only a few years ago from neighboring stars. Others have traveled for millions, even billions, of years before reaching Earth. Each carries information, temperature, composition, motion, magnetic fields, chemical fingerprints, without leaving our planet. Astronomers have learned the atmospheres of distant worlds, measured the masses of invisible planets orbiting other stars, and watched galaxies evolving across cosmic time. The first great revolution came from space telescopes. Earth's atmosphere is a remarkable shield for life, but it's not an ideal window for astronomy. It absorbs many wavelengths of light before they reach the ground. Infrared radiation, ultraviolet light, X-rays, and gamma rays are partially or completely blocked. This is fortunate for biology. It is less convenient for astronomy. By placing telescopes above the atmosphere, scientists gained access to an entirely new universe. The Hubble Space Telescope transformed public understanding of space, not merely through its breathtaking images, but through its extraordinary precision. It revealed distant galaxies in unprecedented detail. It measured the expansion of the universe with increasing accuracy. It observed stars being born inside immense clouds of gas and dust. Most importantly for our story, Hubble reminded us that light is the greatest explorer humanity has ever possessed. Where spacecraft cannot yet travel, photons already have. The next generation of observatories pushed even farther. The James Webb Space Telescope was designed to observe primarily in infrared light, allowing it to peer through clouds of dust that hide regions where stars and planets are forming. Instead of seeing only finished planetary systems, astronomers could begin watching their construction. Around young stars, enormous disks of gas and dust slowly evolve. Within them, tiny particles collide. Small rocks become larger ones. Planetesimals emerge. Eventually, entire planets take shape. These observations answer questions once confined to theory. They also raise new ones. How common are Earth-like worlds? How many planetary systems resemble our own? How many might possess environments capable of supporting life? Only 30 years ago, astronomers could not answer these questions. Today, thousands of exoplanets have been confirmed. Some are gas giants larger than Jupiter. Others orbit so close to their stars that a year lasts only a few days. Still others occupy regions where liquid water could potentially exist on their surfaces. The growing catalogue continues to expand every month. This discovery quietly changes the meaning of interstellar travel. For much of history, humanity knew only one planetary system. Now we know that planets appear to be common throughout the Milky Way. The nearest potentially habitable world may not lie hundreds of light years away. It could be relatively nearby in galactic terms. The challenge is no longer finding destinations. It is reaching them. Spacecraft within our own solar system have also become laboratories for interstellar exploration. Consider the Voyager probes. Although designed to study the outer planets, they eventually became the first human-made objects to enter interstellar space. Their instruments continue measuring the density of charged particles beyond the Sun's protective bubble. They detect subtle changes in magnetic fields. They reveal conditions that future starships may someday encounter. Voyager was never intended to reach another star, yet it has already begun exploring the environment between them. The New Horizons spacecraft, famous for its historic flyby of Pluto, now continues its own journey through the outer solar system. Like Voyager, it contributes valuable information about the distant frontier separating our planetary neighborhood from true interstellar space. Each mission extends our map a little farther. Meanwhile, entirely different tools operate not in space but inside computers. Modern astrophysics relies heavily upon numerical simulations. Some of these calculations require weeks or months on powerful supercomputers. They recreate the birth of galaxies, the collapse of giant molecular clouds, the formation of stars, the evolution of planetary systems, even the interaction between radiation and interstellar dust. Unlike observations, simulations allow scientists to change one variable at a time. What happens if a star forms with slightly greater mass? How does a planetary system evolve if giant planets migrate inward? What becomes of interstellar gas over millions of years? The answers help astronomers interpret what telescopes observe. Observations and simulations work together like two halves of a conversation. One reveals reality, the other tests understanding. Artificial intelligence has recently begun assisting this process. Modern machine learning systems analyze enormous astronomical datasets that would overwhelm individual researchers. Billions of stars, millions of galaxies, countless spectra. Patterns invisible to human eyes sometimes emerge through careful computational analysis. Yet these systems do not replace scientists. They extend their reach. Every surprising pattern still requires physical explanation. Data alone cannot reveal truth without interpretation. Perhaps the most ambitious modern concept aimed directly at interstellar travel is the Breakthrough Starshot initiative. Rather than attempting to launch massive spacecraft carrying human crews, it proposes something far smaller. Tiny robotic probes, each no larger than a small electronic device, attached to ultralight reflective sails. Powerful laser arrays on Earth would accelerate these probes to perhaps 20% of the speed of light. At that velocity, they might reach the Alpha Centauri system in roughly 20 years. No people would travel aboard, only instruments, cameras, sensors, transmitters. The concept remains highly experimental. Many engineering challenges remain unsolved. The lasers do not yet exist at the required scale. The sails have not been demonstrated under such extreme conditions. Communicating across more than 4 light years with miniature spacecraft presents another formidable difficulty. Yet unlike many ideas surrounding interstellar travel, the proposal depends primarily upon known physics rather than unknown laws of nature. It represents an important shift in thinking. Perhaps humanity's first visitors to another star will not resemble the great ships of science fiction. Perhaps they will resemble seeds, tiny, lightweight, extraordinarily fast. The history of exploration often begins with the smallest steps. Looking back, this pattern appears again and again. The first balloons did not carry passengers across oceans. The Wright brothers did not build transcontinental airliners. Sputnik was not a moon mission. Apollo was not a voyage to another star. Progress accumulates. Each generation inherits the discoveries of the previous one. Each extends the frontier a little farther. And yet, despite the astonishing achievements of modern astronomy, one truth remains unchanged. The more carefully we study the cosmos, the more clearly we recognize how much remains unknown. Every telescope uncovers new mysteries. Every spacecraft raises unexpected questions. Every simulation exposes gaps in our understanding. The greatest challenge of interstellar travel may therefore lie not in the technologies we have yet to invent, but in the questions we have not yet learned to ask. There is a quiet moment in the history of every scientific discipline. It arrives when knowledge has advanced far enough to reveal its own boundaries. At first, discovery feels like collecting answers. Each observation replaces uncertainty with understanding. Every new instrument sharpens the picture. The universe gradually appears less mysterious than before. Then something unexpected happens. The clearer the picture becomes, the more empty spaces appear within it. Astronomy has reached that moment. Never before have we known so much about the cosmos. Never before have we been so aware of how much remains beyond our understanding. Interstellar travel sits precisely at that frontier. The challenge is no longer asking whether the stars exist or how far away they are. Those questions have been answered with remarkable precision. The deeper questions remain. Can human beings survive a journey lasting decades beyond the protection of the solar system? Can propulsion systems ever produce enough energy without requiring impossible amounts of fuel? Can biology endure environments unlike anything life has previously encountered? Most importantly, are there physical principles we have not yet discovered that could transform our understanding of the problem itself? Science answers these questions carefully. Sometimes the answer is yes, sometimes no. Most often, the honest answer is simply that we do not yet know. This uncertainty is not a weakness. It is the natural condition of exploration. Consider propulsion. Chemical rockets have been understood for generations. Nuclear fission is well established. Fusion remains an active field of research. Antimatter exists and has been created inside laboratories. These are facts. Whether any of them can become practical systems capable of carrying large spacecraft across interstellar distances remains uncertain. The distinction is subtle but essential. Knowing that something is physically possible does not mean it is technologically achievable. Human flight illustrates this beautifully. Birds demonstrated that powered flight was physically possible for millions of years before engineers learned how to build airplanes. Similarly, nuclear fusion powers every ordinary star in the universe. Yet reproducing that process reliably inside machines on Earth has challenged scientists for decades. Nature often reveals what can be done long before civilizations discover how to do it. Shielding presents another unanswered problem. Researchers understand many of the dangers posed by radiation and relativistic dust impacts. They can estimate the energies involved. They can model the likely damage. Designing materials capable of protecting astronauts for decades without making spacecraft impossibly heavy remains an open engineering challenge. Material science continues advancing every year. Stronger composites, lighter alloys, self-healing polymers, nanostructured materials, each represents meaningful progress. Whether any combination ultimately proves sufficient remains unknown. Life support systems raise equally profound questions. The International Space Station has shown that humans can live in space for months. Future lunar and Martian missions may demonstrate years. An interstellar voyage asks for something fundamentally different. Not survival, sustainability. A spacecraft traveling for several decades becomes a complete ecosystem. Nothing significant can be imported. Nothing essential can be discarded. Every biological cycle must function continuously. Plants, microorganisms, water purification, atmospheric chemistry, waste recycling, and human psychology all become parts of one interconnected system. Earth itself performs this task effortlessly because it is an entire planet. Reproducing that balance inside a spacecraft has never been attempted. Scientists study closed ecological systems with growing sophistication. Some experiments have been highly encouraging. Others have revealed unexpected instabilities. Tiny changes can propagate through complex ecosystems in surprising ways. Understanding those interactions remains an active area of research. Then there is gravity. More precisely, the absence of it. Astronauts returning from long missions often require rehabilitation before walking comfortably again. Bones lose minerals, muscles weaken, the cardiovascular system adapts to weightlessness. Exercise reduces many of these effects. It does not eliminate them entirely. Artificial gravity has therefore become one of the most discussed concepts for long-duration spaceflight. The idea itself is straightforward. Rotate part of the spacecraft. Centrifugal acceleration produces an effect similar to gravity. Physics supports the concept completely. Engineering it efficiently while maintaining structural integrity across decades presents another matter. No rotating habitat designed for human life has yet operated in space. Whether such systems become routine remains to be seen. Psychology introduces perhaps the least predictable uncertainty. Human beings evolved within rich social environments beneath open skies, changing weather, and familiar landscapes. Interstellar crews would experience something profoundly different. A fixed community, a confined environment, no possibility of rescue, no possibility of returning home, no changing horizon. Even communication with Earth would become increasingly delayed. The psychological consequences are difficult to predict because no truly comparable human experience exists. Antarctic research stations offer partial analogies. So do submarines. Long-duration orbital missions contribute valuable insights. None perfectly reproduce decades of irreversible isolation. Another uncertainty lies within biology itself. How does the human body respond to continuous exposure to the deep space radiation environment over many years? Researchers possess estimates based upon current knowledge. They do not yet possess complete answers. Medicine advances by studying real patients. Interstellar travelers do not yet exist. Some questions cannot be fully answered until such journeys begin. There are mysteries beyond engineering as well. Dark matter constitutes most of the matter within galaxies, yet its nature remains unknown. Dark energy appears to dominate the large-scale evolution of the universe. Yet its origin remains one of modern cosmology's deepest puzzles. Neither currently offers an obvious solution for interstellar propulsion, yet history repeatedly reminds us that fundamental discoveries sometimes reshape practical technology in unexpected ways. Electricity once appeared to be a scientific curiosity. Quantum mechanics seemed hopelessly abstract. Today both underpin modern civilization. No responsible scientist would claim that dark matter or dark energy will someday revolutionize space travel. Equally, no responsible scientist can confidently rule out unforeseen consequences of future discoveries. Unknown physics should never be confused with magical solutions, but neither should it be dismissed without evidence. This careful balance defines scientific thinking. Remain open, remain skeptical, demand evidence, accept uncertainty. Perhaps the most important unanswered question is surprisingly philosophical. Not because philosophy replaces science, because it shapes the questions science chooses to pursue. Suppose humanity eventually develops every required technology: reliable propulsion, radiation protection, closed ecosystems, artificial gravity, autonomous intelligence. Should we send people, or would sophisticated robotic explorers accomplish the same scientific goals with far less risk? Robots require no oxygen, no food, no psychological support. They tolerate radiation far better than living organisms. Artificial intelligence grows more capable every decade. Future robotic explorers may possess abilities far beyond those of today's spacecraft. Some scientists therefore argue that humanity's first true interstellar explorers will almost certainly be machines. Others respond that exploration has never been solely about collecting data. Human curiosity carries qualities difficult to quantify: adaptability, creativity, wonder, the ability to notice the unexpected. The debate remains unresolved. Perhaps there is room for both. What is certain is that astronomy has entered an extraordinary age. Never before have we possessed such powerful telescopes, such detailed simulations, such ambitious engineering concepts. And yet, never before has the frontier appeared so vast. The edge of knowledge is not a wall. It is a shoreline. Beyond it lies an ocean we have only begun to glimpse. The farther we sail, the farther the horizon seems to retreat, and somewhere beyond that moving horizon may lie discoveries capable of changing not only how we travel between the stars, but how we understand the universe itself. Every scientific journey eventually reaches a place where observation becomes difficult, not because curiosity fades, but because nature begins withholding its answers. Astronomers call this the frontier. It is not a physical location marked on any map. Rather, it is the boundary separating what can currently be tested from what remains beyond the reach of present technology. Interstellar travel stands squarely upon that boundary. Everything we have explored so far rests upon observations, experiments, and theories that have survived careful testing. We know the speed of light with extraordinary precision. We understand how gravity shapes the motion of planets and stars. We have measured time dilation using atomic clocks and particle accelerators. We have watched galaxies evolve across billions of years. These are among the strongest foundations in modern science. Yet beyond them lie ideas that are simultaneously fascinating and uncertain. They are not fantasies. Neither are they established realities. They occupy the narrow and often misunderstood territory between mathematics and nature. Perhaps the most famous of these ideas is the wormhole. General relativity describes gravity not as a force pulling objects together, but as the curvature of spacetime itself. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. Within Einstein's equations, certain unusual geometries appear possible. Among them are structures that seem to connect distant regions of spacetime through a kind of shortcut, rather than travelling across the enormous distance separating two stars. A traveller passing through such a shortcut could, in principle, emerge near the destination after covering a much smaller path. The idea is captivating. It has inspired novels, films, and generations of scientific discussion. But mathematics alone does not guarantee physical reality. The equations permit many solutions that nature may never realize. The Earth, for example, could theoretically balance on the tip of a pencil if every force were perfectly aligned. Physics allows it. Reality almost certainly does not. Wormholes face a similar challenge. Most mathematical models suggest that a traversable wormhole would require exotic forms of matter possessing properties unlike anything yet observed in sufficient quantities. In particular, many solutions depend upon negative energy density. This phrase is often misunderstood. Negative energy does not simply mean less energy. It refers to very specific conditions in quantum physics where certain mathematical descriptions permit energy densities below what would normally be expected in empty space. Tiny examples of such effects have been observed indirectly through phenomena like the Casimir effect. However, these laboratory-scale observations are unimaginably smaller than what would be required to stabilize a wormhole large enough for a spacecraft. The gap is enormous. It is rather like observing a single droplet of water and asking whether it proves the existence of an entire ocean. The droplet is real. The ocean remains hypothetical. Warp drives occupy a similarly intriguing position. Unlike wormholes, they do not attempt to create shortcuts between distant locations. Instead, they seek to manipulate spacetime itself. In 1994, physicist Miguel Alcubierre published a mathematical solution suggesting that a region of contracted spacetime ahead of a spacecraft and expanded spacetime behind it might effectively carry the craft faster than light relative to distant observers. Inside its local region, the spacecraft would never violate Einstein's speed limit. It would remain essentially at rest within its own bubble of spacetime. The bubble itself would move. This distinction is subtle. Nothing inside the bubble outruns light through local space. Instead, space itself changes. At first glance, this appears to bypass one of the greatest obstacles in physics. Yet every proposed version encounters formidable difficulties. Early calculations suggested that creating such a warp bubble would require amounts of exotic energy comparable to the mass energy of entire planets or even stars. Later refinements reduced these estimates considerably. Even so, the requirements remain far beyond anything remotely achievable with current technology. Equally important, no experiment has ever demonstrated the creation of such a space-time distortion. The concept remains a mathematical possibility. Whether nature permits it in practice is unknown. Quantum gravity introduces another frontier. General relativity describes gravity with extraordinary accuracy on large scales. Quantum mechanics describes atoms and subatomic particles with equal success on the smaller scales. Each theory has survived countless experimental tests. The difficulty is that they do not yet combine into one complete framework. Inside black holes, near the beginning of the universe, possibly within exotic spacetime structures, our present theories become incomplete. Physicists continue searching for a deeper description capable of uniting them. Several approaches exist: string theory, loop quantum gravity, other mathematical frameworks. Each offers valuable insights. None has yet received decisive experimental confirmation. This uncertainty matters because some proposed methods of interstellar travel depend upon aspects of physics that may ultimately emerge only from such a unified theory. Scientists therefore proceed carefully. They distinguish between possibility and probability. A mathematically consistent idea is not automatically a physically realizable one. Another fascinating question concerns the vacuum itself. For centuries, empty space was imagined as nothing at all. Modern quantum field theory paints a more subtle picture. Even what we call a vacuum possesses fluctuating quantum fields. Virtual particles briefly appear and disappear according to the probabilistic nature of quantum mechanics. These fluctuations are not directly visible in the ordinary sense, yet their effects have been measured experimentally. Does this mean empty space contains vast untapped energy? Perhaps. Can that energy be extracted to propel spacecraft? No accepted theory currently shows how. Many popular discussions leap from the existence of quantum fluctuations to claims of limitless propulsion. Physics does not support such conclusions. The existence of a phenomenon does not automatically reveal a practical method of using it. History offers many examples. Lightning existed for billions of years before humanity learned how to generate electricity reliably. Knowledge grows gradually. Speculation alone cannot replace evidence. This careful separation between established science and hopeful imagination is one of astronomy's greatest strengths. Researchers routinely publish ideas that later prove incomplete. Others survive decades of testing before becoming accepted. Neither outcome represents failure. It is simply how science advances. Every hypothesis is an invitation to investigate, not a declaration of truth. Perhaps the most beautiful aspect of the frontier is that it remained open a century ago. No one had measured the expansion of the universe. No one knew galaxies beyond our own existed. Black holes were mathematical curiosities. Exoplanets had never been observed. Today, all are central parts of astronomy. It would therefore be unwise to assume that our present understanding is final. Equally, it would be unwise to assume that every imaginative concept will eventually prove correct. The future almost always surprises us in ways no one predicts. Sometimes the greatest discoveries are not the answers scientists expected. They are the questions nature unexpectedly asks in return. For now, the frontier remains exactly where it should be, a place of careful optimism, a place where mathematics stretches toward possibility, while observation patiently follows behind, and where the future generations ultimately cross 1 light year with advanced propulsion. Ingenious engineering, or methods not yet conceived, they will still inherit the same remarkable lesson. The universe has never surrendered its deepest mysteries easily. Every step toward understanding has required patience, humility, and evidence. Those qualities, more than any engine ever built, may ultimately determine how far humanity is able to travel. There is a quiet assumption that has accompanied humanity throughout history. The assumption is that every frontier eventually becomes ordinary. Mountains once appeared impassable until paths crossed them. Oceans seemed endless until ships learned to navigate by the stars. The sky itself remained forever beyond reach until fragile machines discovered how to fly. Each generation inherited boundaries that seemed permanent. Each generation watched some of those boundaries disappear. It is therefore natural to believe that the stars represent merely the next frontier in the same long story. Perhaps they do, but perhaps they also represent something different. Every challenge we have encountered throughout this journey has pointed toward a remarkable conclusion. Traveling 1 light year is not simply difficult because we have not yet built the right spacecraft. It is difficult because the universe appears to have arranged its fundamental laws in a way that strongly discourages rapid travel across interstellar space, distance, energy, relativity, radiation, time. Every one of them tells the same story. Individually, each obstacle seems manageable. Together, they form something resembling a woven fabric. Remove one thread and another immediately bears the weight. This raises a profound question. What if the greatest lesson of 1 light year is not about engineering at all? What if it is about perspective? For most of human history, civilization has expanded because movement was comparatively inexpensive. Walking carried people across valleys. Ships connected continents. Railroads united nations. Aircraft linked the entire planet within a single day. Communication became even faster. Today, information routinely circles Earth in fractions of a second. Our civilization has grown around the assumption that movement and communication continually become easier. The cosmos offers a striking contrast. Even perfect communication cannot outrun light. Even perfect engineering cannot ignore relativity. The universe seems to encourage knowledge to travel much more readily than matter. This distinction may shape the destiny of every intelligent civilization. Consider astronomy itself. Without traveling beyond Earth, humanity has already observed planets around distant stars. We have measured the atmospheres of some of those worlds. We have photographed galaxies billions of light years away. We have reconstructed much of the history of the universe from the faint light reaching our telescopes. Knowledge has crossed distances that our spacecraft cannot, in a sense. Our understanding already extends far beyond our physical reach. Perhaps this is not a temporary condition. Perhaps it is a permanent feature of cosmic civilization. The philosopher and astronomer Carl Sagan often emphasized that exploration begins with curiosity long before it begins with travel. Modern astronomy demonstrates the truth of that idea. Every improvement in our telescopes has expanded humanity's effective presence throughout the cosmos. A photon arriving from a distant galaxy carries information without requiring us to make the journey ourselves. Every observation becomes a kind of encounter across unimaginable distances. This suggests an intriguing possibility. Advanced civilizations may invest less in transporting themselves physically across the galaxy than in transporting knowledge. Powerful observatories, autonomous robotic explorers, artificial intelligence capable of independent scientific investigation, sophisticated communication networks. These technologies may ultimately prove more practical than fleets of enormous crewed starships. Indeed, humanity is already following this path. Every robotic spacecraft extends our senses rather than our bodies. Voyager continues reporting conditions beyond the heliosphere. Mars rovers investigate environments no human has yet visited. Orbiters map distant moons with extraordinary precision. The James Webb Space Telescope studies galaxies formed shortly after the Big Bang. Our civilization increasingly explores by proxy. This is not a sign of failure. It may represent wisdom. Biological organisms possess remarkable strengths. They also possess significant limitations. Humans require oxygen, water, food, stable temperatures, and protection from radiation. Machines require none of these in the same way. A robotic probe can patiently endure conditions that would quickly overwhelm a crew. Artificial intelligence continues improving at recognizing patterns, adapting to unexpected observations, and making autonomous decisions. While today's systems remain specialized, future generations may become extraordinarily capable scientific explorers. If that occurs, humanity's first meaningful exploration of another stellar system may not involve people at all. It may involve instruments carrying the accumulated knowledge of an entire civilization. Some find this idea disappointing, others find it beautiful. Perhaps both reactions arise because we instinctively associate exploration with human footsteps. History encourages that image. The first explorers crossed deserts, climbed mountains, and sailed oceans in person. Interstellar distances invite a different model. The explorer may become a partnership between biological curiosity and technological capability. Human imagination designs the mission. Machines execute it. Knowledge returns across the light years. Meanwhile, another realization quietly emerges. The difficulty of crossing one light year may also explain something about the apparent silence of the cosmos. Earlier, we considered the possibility that intelligent civilizations exist elsewhere in the Milky Way. Suppose they do. Suppose many have arisen over billions of years. Why does the galaxy not appear filled with obvious signs of their presence? Again, numerous explanations remain possible, but physical distance deserves renewed attention. If every civilization faces essentially the same constraints imposed by relativity and energy, then the expansion of intelligent life may proceed far more slowly than popular imagination often assumes. The Milky Way may not resemble a bustling network of interconnected worlds. Instead, it may resemble an archipelago, countless inhabited islands separated by oceans so vast that direct contact becomes extraordinarily rare. This possibility carries a surprising emotional consequence. It makes our own world appear both smaller and more precious. Earth is not merely the place where humanity originated. It is currently the only place known to support life. Every ecosystem, every language, every work of art, every scientific discovery, every memory, all exist upon a remarkably thin layer surrounding one ordinary planet orbiting one ordinary star. Interstellar distance quietly magnifies the value of home, yet it does not diminish curiosity. If anything, the opposite occurs. Knowing that the stars are extraordinarily difficult to reach does not make them less interesting. It makes every successful observation more meaningful. Every exoplanet discovered, every spectrum analyzed, every spacecraft launched, each becomes another conversation with a universe that refuses to surrender its secrets easily. Perhaps this has always been the deeper purpose of science, not to eliminate mystery, but to replace impossible mysteries with better questions. One light year once appeared to be merely a distance. Now it has become something richer, a lesson about physics, a lesson about civilization, a lesson about humility, and above all, a reminder that understanding the universe often changes our understanding of ourselves. The farther we have looked outward, the more clearly we have begun to see the remarkable fragility and rarity of the world from which every human journey has so far begun. The future has always been difficult to predict. Standing on a shoreline 500 years ago, it would have been almost impossible to foresee satellites orbiting Earth or robotic spacecraft photographing the icy plains of Pluto. Every age naturally assumes that its own understanding is close to complete, only for the next generation to reveal an entirely new horizon. Astronomy teaches humility precisely because of this history, again and again. The universe has proven larger, older, and more surprising than anyone expected. For that reason, looking into the far future requires careful balance. We must distinguish between what current evidence strongly suggests, what appears physically plausible, and what remains pure speculation. The farther we look ahead, the more carefully those boundaries must be respected. One possibility seems remarkably likely. Humanity's first true interstellar explorers will not resemble the great starships of literature. They will be machines. The reasons are practical rather than philosophical. Robotic spacecraft require no atmosphere. They do not need food. They tolerate radiation far better than biological organisms. They can remain dormant for years if necessary. They are becoming increasingly capable of making decisions without immediate human guidance. Even today, spacecraft routinely operate millions of kilometers from Earth with considerable autonomy. Future generations may carry laboratories, telescopes, and sophisticated artificial intelligence across the stars long before human beings do. Such missions could proceed gradually. A tiny robotic probe launched during one century, data returned several decades later. Improved missions built from the lessons learned. Humanity's understanding expanding step by step. History suggests that exploration rarely occurs through a single dramatic leap. It advances through countless small successes accumulated across generations. Another possibility involves permanent human settlements within our own solar system. Before crossing 1 light year, civilization may first become truly multiplanetary. The Moon, Mars, perhaps the icy moons Europa or Titan, where future habitats might one day operate beneath protective shells of ice or within carefully engineered environments. Living successfully beyond Earth would teach lessons impossible to acquire in laboratories alone. Closed ecological systems, long-duration spaceflight, resource recycling, psychological adaptation, autonomous communities. Every challenge solved within the solar system becomes valuable preparation for any future attempt at interstellar travel. In this sense, Mars may be less a destination than a classroom. Some researchers have suggested that patient expansion could continue outward for millions of years, not through fleets of enormous starships, but through a gradual process. One nearby system explored, then another. Each newly established civilization launching missions toward its own neighboring stars. Expansion proceeding like ripples spreading across a pond. The mathematics of such growth is fascinating, even if each individual journey required centuries. A civilization enduring for millions of years could eventually spread across substantial regions of the galaxy. This possibility does not violate relativity. It simply demands extraordinary patience. Whether any civilization can maintain continuity over such immense timescales remains entirely unknown. History offers little guidance. Human civilization, in its present technological form, has existed for only a few centuries. The Milky Way has existed for more than 13 billion years. Our perspective remains remarkably young. The galaxy itself will not remain unchanged during this future. Stars continue forming inside immense molecular clouds. Others quietly exhaust their nuclear fuel. The Sun, now comfortably middle-aged, will slowly become brighter over the next several hundred million years. Eventually, roughly 5 billion years from now, it will expand into a red giant. The inner planets will experience profound changes. Earth's long-term future remains uncertain under those conditions. Whether humanity survives to witness such events depends upon choices and technologies unimaginably distant from our present experience. Interstellar travel, if it ever becomes practical, may eventually transform from curiosity into necessity. Not tomorrow, not next century, but across billions of years, stars themselves evolve. Civilizations wishing to endure indefinitely may ultimately require new homes. This idea rests firmly within accepted stellar evolution. The timescales simply exceed ordinary human intuition. There are other possibilities that remain considerably more speculative. Perhaps future discoveries in physics will reveal new methods of manipulating space-time. Perhaps practical fusion propulsion will become routine. Perhaps advanced laser infrastructure will accelerate countless robotic explorers between neighboring stars. Perhaps none of these will occur. Science cannot honestly predict discoveries that have not yet been made. History repeatedly reminds us that the greatest breakthroughs are often the least anticipated. No astronomer of the 19th century predicted radio astronomy. No physicist of the early 20th century anticipated exoplanet surveys discovering thousands of distant worlds. Progress frequently arrives from unexpected directions. Still, certain boundaries appear remarkably robust. Nothing discovered over the past century has weakened the evidence supporting relativity. On the contrary, every precise experiment has strengthened it. If future civilizations travel between the stars, they will almost certainly do so while respecting the same fundamental speed limit we observe today. Their methods may become astonishingly sophisticated. The laws themselves appear beautifully consistent. Perhaps this consistency carries its own quiet elegance. The universe is not arbitrary. It does not alter its rules simply because intelligent beings wish to travel farther. Instead, it invites civilizations to understand those rules deeply enough to work with them rather than against them. Every successful technology throughout history has followed precisely that path. Airplanes succeed because they cooperate with aerodynamics. Spacecraft succeed because they cooperate with orbital mechanics. Future starships, whatever form they ultimately take, will succeed only by cooperating with the deeper geometry of space-time itself. There is another future worth considering. Not the future of humanity, the future of knowledge. Every observation made today becomes part of an inheritance passed to future generations. The spectra collected by telescopes, the trajectories measured by spacecraft, the equations refined by physicists, the simulations performed by supercomputers, each contributes another piece to a puzzle no single lifetime can complete. Science has always been a conversation extending across centuries. Interstellar exploration may simply continue that conversation across millennia. Perhaps the first people to receive images from another planetary system have not yet been born. Perhaps the engineers who designed the spacecraft carrying those cameras are still generations away. Yet their work has already begun. Every telescope constructed today shortens the distance between ignorance and understanding. Every experiment narrows uncertainty. Every careful question extends humanity's reach a little farther into the cosmos. The future therefore need not arrive all at once. It may unfold quietly. One observation, one discovery, one mission, one generation at a time, and if that is true, then perhaps the greatest achievement of our civilization will not be crossing 1 light year in a single journey. It will be building a chain of knowledge strong enough that each generation can travel a little farther than the one before, until distances that once seemed eternal gradually become chapters in a story still being written. When this journey began, we started with a belief so familiar that it almost escaped notice. Given enough time and sufficiently advanced technology, surely any destination can eventually be reached. It is a deeply human belief. Our history encourages it. Every generation has inherited impossibilities that became ordinary within a few decades. Oceans once marked the edge of the known world. Mountains divided civilizations. The sky itself seemed forever beyond human reach. Again and again, determination appeared to triumph over distance. Now, after travelling through the laws of physics rather than across the stars, that belief looks rather different. Not because it was entirely wrong, but because it was incomplete. The greatest obstacle to crossing 1 light year was never simply the distance itself. Distance is only a number. The real challenge lies in everything that distance quietly demands. It demands energy beyond anything chemical fuels can provide. It demands propulsion systems that remain largely theoretical. It demands protection against radiation that scarcely matters within Earth's atmosphere. It demands navigation of extraordinary precision over trillions of kilometers. It demands patience measured not merely in years, but perhaps in generations. Most remarkably, it demands cooperation with the deeper structure of space-time itself. The farther we have traveled through this story, the more the universe has revealed a remarkable consistency. The speed of light is not merely fast, it is fundamental. Time is not universal, it is relational. Space is not empty, it is filled with subtle hazards and ancient messengers. Knowledge travels with astonishing ease. Matter does not. Every chapter has quietly returned to the same conclusion from a different direction. The universe is neither hostile nor welcoming. It is simply lawful. That distinction matters. Nature does not prevent interstellar travel because it wishes to preserve some cosmic secret. The laws of physics possess no intentions. Gravity does not choose whom to attract. Light does not decide how fast to travel. Relativity does not make exceptions for ambitious civilizations. The universe behaves consistently. Our task has always been to understand those patterns rather than argue against them. There is something unexpectedly comforting about that realization. If the laws of nature changed unpredictably, exploration would become almost impossible. Instead, every successful spacecraft ever launched has relied upon the astonishing reliability of those laws. Engineers calculate trajectories because gravity behaves tomorrow exactly as it behaved yesterday. Astronomers measure distant galaxies because light follows the same principles everywhere we observe it. The very limits that challenge us also make science possible. Perhaps this is why astronomy inspires such quiet confidence. It does not promise easy answers, it promises understandable ones. Along the way, another idea has gradually emerged. Humanity often speaks about conquering space. The phrase sounds bold, yet the history of science suggests something gentler. We have never conquered the ocean. We learned how to sail upon it. We never conquered gravity. We learned how to work with it. Likewise, if humanity someday reaches another star, it will not be because we defeated the universe. It will be because we understood it well enough to cooperate with it. That shift in perspective changes the meaning of exploration. The goal is no longer to overpower nature. It is to become increasingly fluent in its language. Every telescope represents another sentence learned. Every spacecraft, another conversation begun. Every equation, another fragment of a grammar written into reality itself. Viewed this way, crossing one light year ceases to be merely a technological ambition. It becomes an expression of understanding. The better we comprehend the universe, the farther we may eventually travel within it. There is also a quieter lesson hidden beneath the scientific one. Throughout this documentary, the stars have continually reminded us of scale. The Milky Way contains hundreds of billions of stars. The observable universe contains hundreds of billions of galaxies. Distances stretch across numbers so large that ordinary language struggles to contain them. It would be easy to feel insignificant. Astronomy often produces exactly the opposite effect. The atoms forming your body were forged inside ancient stars. The oxygen you breathe, the calcium within your bones, the iron carried through your blood all originated in stellar furnaces long before the sun was born. Human beings are not strangers visiting the cosmos. We are products of it. When astronomers study distant stars, they are, in a profound sense, studying their own ancestry. The universe is not simply around us, it is within us. That connection transforms the meaning of one light year. The nearest star is not merely an unreachable destination. It is another chapter in the same cosmic story that eventually gave rise to Earth. The gulf separating us is enormous. The relationship remains intimate. Perhaps this is why the night sky continues captivating every civilization that has ever existed. Long before telescopes, people looked upward with questions. Who are we? How large is the world? What lies beyond the horizon? Modern astronomy has answered many of those questions. In doing so, it has uncovered even deeper ones. Every generation inherits mysteries from the previous one. The greatest gift science offers is not certainty. It is the ability to ask better questions than before. A century ago, crossing one light year belonged almost entirely to imagination. Today, we understand the physical obstacles with extraordinary clarity. A century from now, future scientists may look back upon our present understanding as merely another early step. That possibility is not wishful thinking. It is the pattern repeated throughout the history of discovery. Knowledge expands, horizons retreat, questions evolve. The universe remains patient as we return to where we began. The original belief has not disappeared. It has matured. Yes, humanity may someday reach another star, but whether that happens will depend not only upon courage or determination. It will depend upon how deeply we continue learning the quiet rules that have governed the cosmos since long before the first stars ignited. And perhaps that is the most remarkable realization of all. The journey toward another light year did not truly begin with rockets. It began the moment human beings first looked into the darkness and wondered what, if anything, could possibly lie beyond it. The nearest star has not moved during the time you have spent listening. It still shines just over 4 light years away. Its light still crosses the darkness at nearly 300,000 kilometers every second. Its planets, if they exist in quiet orbit around it, continue circling their sun with complete indifference to our curiosity. Nothing about the cosmos has changed during this journey, only our understanding has, at the beginning. 1 light year sounded like a single unit of distance, a convenient measurement, a number that could be written in a textbook or displayed on a map of nearby stars. Now it carries a different meaning. It has become a symbol of scale, a reminder of patience, a demonstration of how the laws of physics shape every ambition humanity has ever imagined. We have discovered that the universe is astonishingly generous with beauty. It allows galaxies to bloom across billions of light years. It permits stars to forge the elements of life. It fills the night sky with countless worlds waiting to be understood. Yet it is equally uncompromising. It asks every civilization to pay the same price for crossing great distances. Energy, time, knowledge. There are no shortcuts simply because we desire them. In many ways, this realization is deeply reassuring. The cosmos does not favor one species over another. Its laws apply equally to every atom, every planet, every star, and every civilization that may exist somewhere within the Milky Way. Wherever intelligent life has arisen, it must also confront the speed of light. It must also contend with radiation, gravity, inertia, and time. These are not merely human challenges. They are cosmic ones. Perhaps somewhere tonight, beneath another sky orbiting another sun, another civilization is asking the same questions. They may also wonder whether neighboring stars can ever truly become neighbors. They may calculate the same equations, measure the same constants, encounter the same quiet barriers placed by space-time itself. If so, then despite the enormous distance between us, we would already share something profound, a common curiosity. Throughout history, humanity has often imagined exploration as an act of arrival. The explorer reaches the summit, the sailor reaches the opposite shore, the astronaut lands upon another world. Astronomy gently suggests another interpretation. Sometimes exploration is not defined by where we arrive. Sometimes it is defined by how completely we learn to understand what lies between. The empty space separating stars once appeared featureless. Now we know it contains drifting atoms, magnetic fields, cosmic rays, ancient dust, and the faint echoes of stellar evolution. It is not a blank page. It is a landscape, invisible, immense, and quietly alive with physical processes unfolding over millions of years. The journey has changed our understanding of time as well. Human lives are measured in decades. Civilizations endure for centuries. Stars shine for billions of years. Galaxies evolve across spans almost beyond comprehension. Interstellar travel forces these different clocks into the same conversation. A voyage that feels impossibly long to one generation may appear remarkably brief against the lifetime of a star. The universe does not hurry. Perhaps that is one of its greatest lessons. Nature accomplishes extraordinary things through patience. Mountains rise grain by grain. Continents drift centimeter by centimeter. Stars form atom by atom. Galaxies assemble over billions of years. Nothing in the cosmos suggests that greatness requires speed, only persistence. That perspective reshapes our own place within the story. Human civilization is still young. The scientific revolution occupies only a tiny fraction of recorded history. The space age itself is younger than many people alive today. Voyager 1, now traveling through interstellar space, has spent less than a human lifetime making its outward journey. Measured against the age of the Milky Way, these achievements have occurred almost instantaneously. Perhaps we sometimes expect too much from our first steps. The children who watched the Apollo moon landings grew old before seeing humans return beyond low Earth orbit. To some, this felt like stagnation. Astronomy tells a different story. During those same decades, humanity discovered thousands of planets around distant stars, mapped the cosmic microwave background with extraordinary precision, observed black holes directly, detected gravitational waves, built telescopes capable of looking back toward the earliest epochs of the universe. Our reach has expanded enormously, even while our physical presence has remained close to home. Knowledge has continued its voyage, and perhaps knowledge has always been the fastest traveller of all. A single observation can cross generations. An equation written centuries ago can still guide spacecraft today. A beam of starlight that began its journey before human civilization existed can alter our understanding the moment it enters a telescope. Ideas ignore many of the limitations that constrain physical objects. They accumulate. They spread. They endure. In this way, every astronomer, engineer, mathematician, and curious observer becomes part of an expedition that began long before any of us were born. An expedition not toward a particular destination, but toward a deeper understanding of reality itself. 1 light year is therefore more than a distance. It is a teacher. It reminds us that the universe is vast enough to inspire humility, ordered enough to reward reason, and mysterious enough to ensure that curiosity never reaches its destination. Every answer opens another question. Every discovery reveals another horizon. Every solved mystery quietly uncovers one that was previously invisible. Perhaps that endless unfolding is the true gift of astronomy. Not certainty, wonder grounded in evidence, curiosity disciplined by patience, imagination guided by reality. Long after this documentary ends, the stars will continue their silent motions across the night. The photons leaving them this very moment will spend years crossing the darkness before arriving here. Future generations will receive that ancient light, ask new questions, build new instruments, and continue a journey that has no final chapter. Whether humanity someday crosses 1 light year or not, we have already taken the most important step. We chose to ask, and in asking, we became participants in one of the oldest conversations in the universe, a conversation between a curious species and the endless sky above it. The distance remains immense, the destination remains far away, but understanding has always been its own extraordinary form of travel.